What if the universe itself is alive, pulsing with an invisible force that shapes everything from the smallest atom to the largest galaxy? Cosmic energy, the mysterious, omnipresent power that fuels the cosmos, is more than just a scientific concept. It's the heartbeat of existence, driving the birth of stars, bending the fabric of space-time, and weaving the very tapestry of reality. And yet, despite its profound influence, most of us barely scratch the surface of understanding how it works. Today, we're diving deep into the wonders of cosmic energy, uncovering 50 mind-blowing revelations that will challenge everything you thought you knew about the universe. From the secrets of black holes to the hidden connections between energy and consciousness, this journey will take you to the edge of what science can explain and beyond. So, are you ready to explore the forces that could hold the key to understanding not just the cosmos, but our very existence? Let's begin. Imagine the universe not as a collection of isolated objects, but as a living, breathing network, a cosmic energy web where every star, every planet, and every galaxy is a glowing node, intricately connected by invisible threads of energy. This isn't science fiction, it's the way the cosmos actually works. Just as neurons in your brain form connections to create thoughts, the universe weaves its own tapestry of energy, linking regions that are billions of light years apart. This energy flows through the very fabric of space-time, a dynamic force that shapes everything from the birth of stars to the clustering of galaxies. At the heart of this web lies one of the greatest mysteries of modern science: dark energy. This enigmatic force is pushing the universe to expand faster and faster, stretching the cosmic web thinner and thinner over time. Think of it like an invisible hand, gently but relentlessly pulling the threads of the universe apart. Without dark energy, the cosmos as we know it wouldn't exist. It's the driving force behind the ever-growing expanse of space. What's truly fascinating is how this cosmic energy web influences the formation of celestial structures. Galaxies aren't just scattered randomly, they form along the filaments of this web, clustering at the intersections like beads on a string. These intersections become hubs of cosmic activity, where stars ignite, black holes devour, and galaxies collide. It's almost as if the universe has its own blueprint, a grand design written in the language of energy. And here's a thought that might blow your mind. If the cosmic energy web is the universe's nervous system, could it also hold clues about how the cosmos thinks? Could the flow of energy between galaxies be a kind of cosmic communication, a way for the universe to maintain balance and order on the grandest scale? The parallels between the cosmic web and the human brain are striking, hinting at a deeper, almost poetic connection between the micro and the macro. As we continue to explore this vast energy network, one thing becomes clear: the universe is far more interconnected than we ever imagined, and this is just the beginning. The cosmic energy web isn't just a backdrop for the stars. It's the stage on which the entire drama of the universe unfolds. Now, let's zoom in a little closer and explore how cosmic energy shapes the very building blocks of the universe, galaxies. These colossal structures, home to billions of stars, planets, and cosmic phenomena, don't just appear out of nowhere. They're sculpted by the invisible hands of cosmic energy, a force that orchestrates their birth, growth, and evolution over billions of years. At the core of this process is gravitational energy, the universe's great architect. Picture this: in the early universe, tiny ripples in the fabric of space-time, like waves on the surface of a vast cosmic ocean, began to pull matter together. Over time, gravity amplified these ripples, drawing gas, dust, and dark matter into dense clumps. These clumps became the seeds of galaxies, growing larger and more complex as they sucked in more material from their surroundings. But gravity isn't the only player in this cosmic dance. magnetic fields, often overlooked, play a crucial role in shaping galaxies into the intricate structures we observe today. These invisible fields thread through space, guiding the flow of charged particles and influencing how stars and gas clouds move. Without them, galaxies might look very different, less organized, less dynamic. Think of magnetic fields as the invisible scaffolding that holds a galaxy together, shaping its spiral arms, central bulges, and even the jets of energy streaming from its core. And then there's dark matter, the enigmatic substance that makes up about 85% of the universe's mass. While it doesn't interact with light, dark matter's gravitational pull is immense, creating the cosmic glue that binds galaxies into clusters. These clusters, in turn, are connected by the filaments of the cosmic web we explored earlier, forming the largest structures in the universe. Dark matter and cosmic energy work in tandem, with dark matter providing the gravitational framework and cosmic energy driving the expansion and movement of these colossal structures. Take our own Milky Way, for example. This sprawling spiral galaxy, home to our solar system, is a masterpiece of cosmic engineering. Its graceful arms, filled with stars and glowing gas clouds, are shaped by the interplay of gravity, magnetic fields, and dark matter. At its center lies a supermassive black hole, a gravitational powerhouse that influences the entire galaxy's structure and behavior. Without the intricate balance of these forces, the Milky Way as we know it simply wouldn't exist. But here's where it gets even more fascinating. Cosmic energy doesn't just shape galaxies, it also fuels the life cycle of stars within them. From the fiery birth of a star in a collapsing gas cloud to its dramatic death as a supernova or black hole, cosmic energy is the driving force behind these celestial transformations. And that's a story we'll dive into next, as we explore how cosmic energy breathes life into the stars and, in turn, the universe itself. At the heart of every star lies a cosmic alchemy lab, where matter is transformed into energy on a scale so vast it defies imagination. Stars are the universe's ultimate energy factories, harnessing the power of nuclear fusion to light up the cosmos. Take our Sun, for instance. Deep within its core, temperatures soar to millions of degrees, creating the perfect conditions for hydrogen atoms to collide and fuse into helium. This process, known as nuclear fusion, releases an astonishing amount of energy, enough to power the Sun for billions of years. Every second, the Sun converts 4 million tons of matter into pure energy, radiating it outward in the form of light and heat. But the story doesn't end there. This energy doesn't just stay trapped within the star. It travels across the void of space, reaching planets, moons, and even life forms like us. Without the Sun's energy, Earth would be a frozen, lifeless rock. It's this same cosmic energy that drives photosynthesis in plants, fuels weather systems, and even powers the technology we rely on every day. In a very real sense, we are all children of starlight, born from the energy forged in the hearts of stars. Yet, stars don't just create energy, they also transform it. When a massive star exhausts its fuel, it doesn't fade quietly into the night. Instead, it explodes in a cataclysmic event known as a supernova. These explosions are among the most energetic phenomena in the universe, releasing more energy in a few seconds than our Sun will produce in its entire lifetime. But supernovae do more than just dazzle. They scatter heavy elements like gold, uranium, and iron across the cosmos, seeding the universe with the building blocks of planets, moons, and even life. This duality, creation and destruction, lies at the heart of cosmic energy. Stars are not only engines of life but also agents of transformation. They forge the elements that make up our world, and when their time comes, they scatter those elements back into the void, setting the stage for new stars, new planets, and new possibilities. And here's the kicker: the energy released by stars doesn't just vanish after a supernova. it ripples through the universe, influencing the formation of new stars and galaxies. In this way, cosmic energy is a perpetual cycle, a force that both builds and rebuilds the cosmos. From the fiery birth of a star to the explosive death of a supernova, energy is the thread that ties the universe together, shaping its past, present, and future. So, the next time you look up at the night sky, remember this: the light you see is more than just a distant glow. It's the legacy of stars, a testament to the incredible power of cosmic energy. And as we continue our journey, we'll uncover even more ways this energy shapes the universe and perhaps even ourselves. Picture a cosmic whirlpool spinning with such ferocity that nothing, not even light, can escape its pull. This is a black hole, one of the most extreme and fascinating phenomena in the universe. Far from being just empty voids, black holes are cosmic energy sinks, regions where matter and energy are compressed to unimaginable densities. They are the ultimate expression of cosmic energy's power, bending the very fabric of space-time and reshaping the universe around them. At the center of a black hole lies the singularity, a point where gravity becomes infinitely strong. Here, the laws of physics as we know them break down, and time itself warps beyond recognition. Surrounding the singularity is the event horizon, the point of no return. Once anything crosses this boundary, it's gone forever, or so we once thought. But black holes aren't just cosmic vacuum cleaners. They're also dynamic engines capable of releasing vast amounts of energy in spectacular ways. One of the most dramatic displays of this energy comes in the form of jets. As matter spirals into a black hole, it doesn't just disappear quietly. Instead, it forms an accretion disk, a swirling, superheated ring of gas and dust. Magnetic fields and intense friction within this disk generate enormous amounts of energy, some of which is ejected in powerful jets that shoot out at nearly the speed of light. These jets can stretch for millions of light years, lighting up the cosmos with their brilliance and shaping the galaxies around them. But that's not all. Black holes also emit radiation, a phenomenon predicted by physicist Stephen Hawking. Known as Hawking radiation, this energy is created when pairs of particles spontaneously form near the event horizon. Occasionally, one particle falls into the black hole while the other escapes, carrying away a tiny bit of the black hole's energy. Over unimaginably long timescales, this process can cause a black hole to slowly evaporate, a concept that challenges our understanding of these seemingly indestructible objects. Imagine a black hole as a cosmic energy recycler. It devours matter, compresses it to its limits, and then releases energy back into the universe in the form of radiation and jets. This cycle isn't just a destructive force, it's a transformative one, reshaping the cosmos and influencing the evolution of galaxies. And here's where the mystery deepens. Black holes may hold clues to the very nature of the universe itself. Some scientists speculate that the information swallowed by a black hole isn't lost forever but encoded in some way, perhaps on the event horizon itself. This idea hints at a profound connection between black holes and the fundamental laws of physics, a puzzle that could unlock new understandings of space, time, and energy. As we peer into the depths of these enigmatic objects, one thing becomes clear. Black holes are not just cosmic oddities. They are key players in the grand story of the universe, shaping its past, present, and future. And as we continue to unravel their secrets, we may find that they hold the answers to some of the biggest questions in science. While black holes captivate us with their intense gravitational pull, there's another cosmic force at work on an even grander scale, one that's stretching the universe itself. This force is dark energy, and it's responsible for one of the most astonishing discoveries in modern cosmology, the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy acts as a kind of cosmic repulsion, pushing galaxies apart at ever-increasing speeds. Imagine the universe as a balloon being steadily inflated. Every dot on the balloon's surface represents a galaxy, and as the balloon expands, the dots move farther apart. This is exactly what's happening on a cosmic scale. The space between galaxies isn't just growing, it's growing faster and faster, driven by the relentless push of dark energy. What makes this so remarkable is that it defies our intuitive understanding of gravity. Gravity, as we know it, is a force of attraction pulling objects together. But dark energy seems to work in the opposite direction, acting as a kind of anti-gravity that stretches the fabric of spacetime itself. Scientists estimate that dark energy makes up about 68% of the universe's total energy, dwarfing even the influence of dark matter and ordinary matter combined. The implications of this expansion are profound. If dark energy continues to dominate, the universe could eventually become a vast, cold, and empty place. Galaxies would drift so far apart that their light would never reach us, leaving the night sky dark and featureless. This scenario, often called the Big Freeze, paints a stark picture of the cosmos's distant future. But here's where it gets even more intriguing. Dark energy isn't just shaping the universe on a grand scale, it's also intimately connected to the smallest scales of existence. The same energy that pushes galaxies apart may also influence the behavior of particles at the quantum level, hinting at a deeper unity between the cosmos and the microscopic world. As we continue to explore the mysteries of dark energy, one thing is certain. It's a force that challenges our understanding of the universe and our place within it. And while its ultimate nature remains elusive, its effects are undeniable, reminding us that the cosmos is a dynamic, ever-changing tapestry woven by the interplay of forces both seen and unseen. In the vast emptiness of space, where it seems like nothing exists, something extraordinary is happening. Cosmic energy is at work, even in the void. This brings us to our sixth revelation. Quantum fluctuations are cosmic energy in action. These tiny, unpredictable ripples in the fabric of spacetime are anything but random. They're the universe's way of saying that even in nothingness, energy is constantly bubbling beneath the surface. Picture a calm pond on a windless day. At first glance, the water appears perfectly still, but if you look closely, you'll notice tiny ripples forming on the surface, seemingly out of nowhere. These ripples aren't caused by wind or fish, they're the result of energy fluctuations, small disturbances that appear and vanish in an instant. Now imagine the vacuum of space as that pond. Even in the absence of matter, energy is constantly flickering in and out of existence, creating what scientists call quantum fluctuations. These fluctuations aren't just theoretical curiosities, they have real, tangible effects. One of the most fascinating outcomes is the spontaneous creation of particle-antiparticle pairs. Out of seemingly nothing, a particle and its antimatter counterpart pop into existence, only to collide and annihilate each other moments later. It's as if the universe is playing a cosmic game of peek-a-boo, constantly creating and destroying tiny pieces of itself. But here's where it gets even more mind-blowing. These quantum fluctuations played a crucial role in shaping the early universe. During a period known as cosmic inflation, when the universe expanded faster than the speed of light, these tiny ripples were stretched across vast distances. What started as microscopic fluctuations became the seeds for the largest structures in the cosmos: galaxies, galaxy clusters, and even the cosmic web itself. Think of it like this: if the universe is a canvas, quantum fluctuations are the first brushstrokes, the subtle marks that eventually grow into a masterpiece. Without these tiny disturbances, the universe might have remained a featureless void, devoid of the complexity and beauty we see today. And this leads us to an even bigger question. Could these fluctuations hold the key to understanding the origins of the universe itself? Some scientists believe that the same quantum processes that created particle-antiparticle pairs might also explain how the universe sprang into existence from nothing. It's a tantalizing idea, one that blurs the line between physics and philosophy, and it brings us closer to unraveling the ultimate mystery of how everything began. So, the next time you gaze up at the night sky, remember this: even in the seeming emptiness of space, cosmic energy is at work, weaving the fabric of reality one quantum ripple at a time. And as we continue to explore these fluctuations, we may find that they hold the answers to some of the universe's deepest secrets. Now, let's travel back in time to the very beginning, the moment when the universe as we know it burst into existence. The Big Bang wasn't just an explosion. It was the ultimate release of cosmic energy, a cataclysmic event that set the stage for everything we see today. Imagine a single point smaller than an atom, packed with unimaginable energy. In an instant, this energy erupted, expanding faster than the speed of light and creating the fabric of spacetime itself. This wasn't just a random burst, it was a finely tuned explosion that laid the foundation for the universe's structure. The energy released during the Big Bang didn't just create matter, it shaped the very laws of physics. From gravity to electromagnetism, the forces that govern our world were born in those first moments, woven into the fabric of reality by the immense power of cosmic energy. But how did this chaotic explosion lead to the orderly universe we observe today? Enter cosmic inflation, a theory that explains how the universe expanded so rapidly that it smoothed out irregularities, creating a remarkably uniform cosmos. Think of it like blowing up a balloon. As it inflates, any small wrinkles on its surface stretch out, becoming almost invisible. In the same way, cosmic inflation stretched the universe, distributing energy and matter evenly and setting the stage for the formation of galaxies, stars, and planets. What's truly astonishing is that we can still detect echoes of this primordial energy today. The cosmic microwave background radiation, a faint glow that fills the universe, is like a snapshot of the Big Bang's aftermath. It's the oldest light in existence, a remnant of that initial burst of energy, and it carries clues about the universe's earliest moments. This energy didn't just shape the cosmos, it also set the conditions for life itself. The elements forged in the hearts of stars, the delicate balance of forces that allows planets to form, even the structure of atoms, all of it traces back to that initial release of cosmic energy. In a very real sense, we are all products of the Big Bang, living in a universe born from an unimaginable surge of power. And here's the kicker: the story of cosmic energy doesn't end with the Big Bang. Its influence continues to shape the universe, driving the expansion of space, fueling the birth of stars, and even influencing the behavior of particles at the quantum level. As we peel back the layers of this cosmic mystery, we're reminded that the universe is a dynamic, ever-evolving tapestry, woven together by the threads of energy that have existed since the very beginning. So, the next time you look up at the night sky, remember this: you're not just looking at stars and galaxies, you're witnessing the ongoing legacy of a cosmic energy that has shaped everything, from the tiniest particles to the vastness of space itself. And as we continue our journey, we'll uncover even more ways this energy connects us to the very heart of the universe. Imagine holding a photograph from the very first moments of your life, a snapshot that captures the raw energy and potential of your existence. Now picture the universe having its own version of that photograph. This is the cosmic microwave background radiation, or CMB, the oldest light in the cosmos. It's a faint glow that permeates every corner of the universe, a relic from the Big Bang that tells the story of how it all began. Discovered by accident in 1965 by astronomers Arno Penzias and Robert Wilson, the CMB was initially dismissed as mere interference, a mysterious noise in their radio telescope. But this noise turned out to be one of the most profound discoveries in science. It's the afterglow of the Big Bang, the moment when the universe transitioned from a seething, opaque plasma to a transparent expanse filled with light. This radiation has been traveling through space for nearly 14 billion years, carrying with it the secrets of the universe's infancy. Think of the CMB as a cosmic time capsule. It's like an ancient photograph, faded but still legible, that captures the universe when it was just a few 100,000 years old. Back then, the cosmos was a hot, dense soup of particles and energy. As the universe expanded and cooled, light could finally travel freely, and those first photons have been racing through space ever since. Today, we detect them as microwave radiation, a faint whisper from the dawn of time. But the CMB isn't just a historical curiosity, it's a treasure trove of information. By studying its subtle variations, tiny differences in temperature across the sky, scientists have pieced together a detailed map of the early universe. These variations are like cosmic fingerprints, revealing the seeds of all the structures we see today: galaxies, galaxy clusters, and the vast cosmic web. Without these initial ripples, the universe might have remained a featureless void. Here's where it gets even more fascinating. The CMB doesn't just tell us about the past, it also gives us clues about the universe's future. The patterns in this ancient light help us understand the composition of the cosmos, including the elusive dark energy that's driving its accelerated expansion. In a way, the CMB is like a cosmic crystal ball, offering glimpses of both where we've come from and where we're headed. And while the CMB is a snapshot of the universe's infancy, it's also a reminder of how cosmic energy continues to shape everything around us. From the birth of stars to the expansion of galaxies, the echoes of the Big Bang are still resonating, influencing the cosmos in ways we're only beginning to understand. So, the next time you hear about the cosmic microwave background, think of it not just as an ancient glow, but as a living testament to the universe's ongoing story, a story written in the language of energy, light, and time. And as we continue to decode its message, we may find that it holds the key to understanding not just our origins, but the very nature of reality itself. Time as we experience it feels constant, a steady, unchanging flow from one moment to the next. But what if time itself is more flexible than we think? What if cosmic energy, the very force that shapes stars and galaxies, also has the power to warp time? This brings us to our ninth revelation. Cosmic energy doesn't just influence space, it bends time itself. At the heart of this idea is Einstein's theory of relativity, which tells us that time isn't absolute. Instead, it's a dimension woven into the fabric of space-time, and that fabric can stretch, twist, and warp under the influence of energy and gravity. Massive objects like black holes and neutron stars act as cosmic time machines, slowing down time in their vicinity. The closer you get to one of these objects, the more time stretches, creating a phenomenon known as time dilation. Let's break this down with a thought experiment. Imagine you're an astronaut orbiting a black hole. From your perspective, time passes normally. You're living your life at the usual speed. But for someone watching you from a safe distance, your movements would appear to slow down. Hours for you might feel like years for them. This isn't just science fiction. It's a real effect predicted by Einstein's equations and confirmed by experiments here on Earth. But why does this happen? It all comes down to energy. Black holes and neutron stars are so dense, so massive, that they warp space-time to an extreme degree. Their immense gravitational pull doesn't just tug on objects, it stretches time itself. The more energy concentrated in one place, the more dramatic the effect. It's as if these cosmic giants are dragging time along with them, slowing it down like a cosmic hand gently pressing on a clock's ticking hands. Now consider the implications of this for space travel. If we could harness the power of time dilation, a journey to a distant star might take only a few years for the travelers, while centuries pass on Earth. It's a mind-bending concept that challenges our understanding of reality. Could time dilation one day make interstellar travel a reality, or does it reveal deeper truths about the nature of time itself? And here's where it gets even more fascinating. Time dilation isn't just a quirk of massive objects. It's a fundamental feature of the universe, a reminder that time and space are deeply intertwined. This connection hints at a reality far more complex than we can perceive, where the flow of time isn't fixed but fluid, shaped by the energy that fills the cosmos. As we ponder these ideas, one question lingers. If cosmic energy can warp time, what does that mean for the nature of reality itself? Could time be just one thread in a larger cosmic tapestry, woven together by the forces that govern the universe? These are questions that push the boundaries of science and philosophy, inviting us to rethink our place in the cosmos. But the story doesn't end here. Just as cosmic energy bends time, it also shapes the very fabric of space, a revelation that takes us even deeper into the mysteries of the universe. And that's where our journey continues next. Space isn't just an empty stage where the drama of the cosmos unfolds. It's an active participant, shaped and molded by the forces that fill it. This brings us to our 10th revelation. Cosmic energy doesn't just warp time, it bends space itself. Imagine the universe as a vast, invisible fabric, and every object within it, stars, planets, black holes, sits on that fabric like a weight. The heavier the object, the deeper it sinks, creating what scientists call a gravitational well. These wells don't just pull matter, they warp the very structure of space around them. To visualize this, think of a trampoline. Place a bowling ball in the center, and the fabric stretches downward, forming a deep curve. Now roll a marble across the trampoline, and you'll notice its path bends as it approaches the bowling ball. This is exactly how massive objects like stars and black holes distort space. They create curves in the fabric of spacetime, bending the paths of anything that comes near, including light itself. This bending of light, known as gravitational lensing, is one of the most fascinating effects of spacetime curvature. When light from a distant star or galaxy passes near a massive object, it doesn't travel in a straight line. It follows the curve of spacetime like a car following a winding road. From our perspective, this can create some truly mind-bending phenomena. For instance, a single galaxy might appear as multiple images, or a distant star might suddenly seem brighter, as if magnified by an invisible cosmic lens. Gravitational lensing isn't just a cool trick of physics, it's a powerful tool for astronomers. By observing how light bends around massive objects, scientists can map the distribution of dark matter, uncover hidden galaxies, and even test the predictions of Einstein's theory of relativity. It's like the universe has handed us a magnifying glass, allowing us to see farther and deeper than ever before. But here's where it gets even more intriguing. Spacetime curvature isn't just a passive effect, it's a dynamic force that shapes the evolution of the cosmos. The gravitational wells created by galaxies and clusters act as cosmic hubs, drawing in matter and energy, fueling the birth of stars and sculpting the large-scale structure of the universe. Without these curves in spacetime, the cosmos as we know it wouldn't exist. And as we explore these ideas, a tantalizing question emerges. Could spacetime curvature hold the key to unlocking the universe's deepest mysteries? From the nature of dark energy to the origins of cosmic structure, the way space bends and twists might reveal clues about the fundamental forces that govern reality. It's a reminder that the universe is far more interconnected than we ever imagined, a place where energy, space, and time are woven together in an intricate cosmic dance. So, the next time you gaze at the stars, remember this. The light you see isn't just traveling through space, it's navigating a vast, warped landscape shaped by the energy that fills the cosmos. And as we continue to explore this landscape, we may find that it holds the answers to some of the biggest questions in science. What if the universe was like a grand orchestra, with every force of nature playing its part in a cosmic symphony? From the gentle pull of gravity to the explosive power of nuclear reactions, these forces seem distinct, but they all share a common origin: cosmic energy. This brings us to our 11th revelation. Cosmic energy is the source of all forces, the invisible thread that ties together the very fabric of reality. Think of gravity, the force that keeps planets in orbit and binds galaxies together. It's not just a mysterious pull, it's a manifestation of energy warping spacetime, creating the curves we explored earlier. Then there's electromagnetism, the force behind light, electricity, and magnetism. At its core, electromagnetism is the result of charged particles exchanging energy, creating the invisible fields that power everything from your smartphone to the northern lights. But the story doesn't stop there. Deep within the nucleus of an atom, two more forces come into play: the strong nuclear force, which holds protons and neutrons together, and the weak nuclear force, responsible for radioactive decay. These forces may operate on an incredibly small scale, but they're just as vital as gravity and electromagnetism. Without them, atoms would fall apart, and the universe as we know it would cease to exist. What's truly remarkable is how these forces are all interconnected, each one a different expression of cosmic energy. It's like the instruments in an orchestra. Each plays a unique role, but together they create a harmonious whole. Scientists have long sought to uncover the deeper connections between these forces, searching for a unified theory that explains them all as different facets of a single, underlying energy. This quest for unity has led to some of the most groundbreaking ideas in physics, from Einstein's theory of relativity to the development of quantum mechanics. Yet, despite decades of research, the ultimate theory, often called the theory of everything, remains elusive. Why? Because cosmic energy operates on scales and in ways that challenge our understanding of the universe. Take gravity, for example. While it dominates the cosmos on large scales, it's incredibly weak compared to the other forces. Electromagnetism, on the other hand, is much stronger but only acts over short distances. The strong nuclear force is even more powerful, but its influence is limited to the tiny realm of atomic nuclei. These differences hint at a deeper complexity, a cosmic puzzle that scientists are still piecing together. And here's where it gets even more fascinating. Cosmic energy doesn't just shape these forces, it also influences the behavior of particles. From the way electrons orbit an atom to the way photons travel through space, energy is the driving force behind every interaction. It's as if the universe is a vast network of energy exchanges, with particles constantly communicating through these fundamental forces. So, the next time you marvel at the stars or flip on a light switch, remember this: you're witnessing the incredible power of cosmic energy, the source of all forces that shape our world. And as we continue to explore this symphony of forces, we may uncover even deeper truths about the universe and our place within it. Now, let's zoom way into the subatomic world, where cosmic energy plays a role so profound it shapes the very building blocks of matter. Imagine a bustling cosmic dance floor where particles whirl and collide, exchanging energy in a choreography that defines the universe's smallest scales. This is the realm of particle physics, where cosmic energy isn't just a passive force, it's the director of the show, guiding how particles move, interact, and even come into existence. Take particle collisions, for example. In places like the Large Hadron Collider, scientists accelerate particles to nearly the speed of light, smashing them together with incredible force. These collisions release bursts of energy so intense that they create entirely new particles, some of which might only exist for a fraction of a second before disappearing again. It's like throwing a pebble into a still pond and watching ripples form, except in this case, the ripples are new forms of matter, born from the energy of the collision. But how do these particles gain their mass, their weight in the cosmic dance, enter the Higgs field, an invisible energy field that permeates the entire universe? Think of it as a kind of cosmic molasses, a thick, syrupy medium that particles move through. Some particles, like quarks and electrons, interact strongly with this field, slowing them down and giving them mass. Others, like photons, glide through it effortlessly, remaining massless. Without the Higgs field, particles would zip through the universe at the speed of light, never forming the stable structures that make up atoms, molecules, and ultimately everything we see around us. Here's where it gets even more fascinating. The Higgs field isn't just some abstract concept, it's a tangible manifestation of cosmic energy. When particles interact with it, they're essentially tapping into the universe's energy reservoir, borrowing a bit of its power to give themselves substance. It's as if the universe has its own cosmic bank, and particles are withdrawing energy to buy their mass. And this energy exchange isn't just limited to the Higgs field. Every particle interaction, from the gentle push of electrons in an atom to the explosive collisions in a supernova, is a transfer of cosmic energy. These interactions are the heartbeat of the universe, the rhythmic pulses that keep the cosmic dance alive. So, what does this mean for our understanding of matter? It suggests that cosmic energy isn't just a background force, it's woven into the very fabric of reality, shaping the particles that make up stars, planets, and even us. And as we continue to explore this intricate dance, we may uncover deeper connections between energy, matter, and the fundamental nature of existence itself. But the story doesn't end here. If cosmic energy shapes particles, could it also hold the key to unraveling the ultimate mystery of matter, why it exists at all? That's the question we'll explore next as we dive deeper into the cosmic web of energy and its role in the universe's grand design. Let's take a moment to consider something truly extraordinary. The very stars in the sky, the ground beneath your feet, even the air you breathe, all of it is made of matter. But what if I told you that matter is just another form of cosmic energy? This is the essence of Einstein's famous equation, E equals mc squared, a simple yet profound statement that forever changed our understanding of the universe. It tells us that energy and matter are two sides of the same cosmic coin, interchangeable and deeply connected. Think of it like this: energy can transform into matter, and matter can transform back into energy. It's not magic, it's physics. The equation shows that even a tiny amount of matter contains an immense amount of energy. To put it in perspective, the energy locked within a single grain of sand, if fully released, could power a city for days. This principle isn't just theoretical, it's the foundation of nuclear reactions where matter is converted into energy on a staggering scale. Take the sun, for example. Every second, it converts millions of tons of its own mass into energy through nuclear fusion. This process powers the sun, giving us light, warmth, and the energy that sustains life on Earth. But the sun is just one star among billions, each one a cosmic powerhouse turning matter into energy. On an even grander scale, supernova, the explosive deaths of massive stars, release so much energy that they briefly outshine entire galaxies. In those moments, matter is transformed into energy on an unimaginable scale, scattering heavy elements across the cosmos and seeding the universe with the building blocks of planets, moons, and even life itself. This relationship between matter and energy doesn't just shape the cosmos, it shapes our everyday lives. Nuclear power plants, for instance, harness the energy stored within atomic nuclei, providing electricity to millions of homes. Even the warmth you feel from a cup of coffee is the result of energy being released at the molecular level. On a cosmic scale, this interplay between matter and energy drives the evolution of stars, galaxies, and the universe itself. But here's where it gets even more fascinating. Cosmic energy doesn't just create matter. It influences how matter behaves. The same principles that govern nuclear reactions also shape the behavior of light, the fundamental messenger of the universe. Light, after all, is pure energy traveling across the cosmos at the speed of light and carrying with it the stories of stars, galaxies, and the very fabric of spacetime. So, the next time you look at the world around you, remember this. Everything you see, touch, and experience is a manifestation of cosmic energy, a force that binds the universe together and drives its endless dance of creation and transformation. And as we continue to explore this relationship, we'll uncover even more ways that energy shapes the cosmos and perhaps even ourselves. What if the universe had a speed limit, a cosmic rulebook that nothing, not even light, could break? This brings us to our 14th revelation, cosmic energy and the speed of light. Light, the fastest thing in the universe, zips through space at an astonishing 300,000 kilometers per second. But this speed isn't just a random number. It's a fundamental constant, a cornerstone of the laws that govern the cosmos. And behind this speed limit lies a profound connection to cosmic energy, one that shapes how we understand everything from the behavior of light to the very fabric of spacetime. Let's start with a simple question. Why does light travel at this speed and not faster or slower? The answer lies in the relationship between energy, mass, and the structure of spacetime itself. According to Einstein's theory of relativity, the speed of light isn't just a limit, it's a boundary that defines the universe. Nothing with mass can reach this speed because as an object accelerates, its energy increases and so does its mass. At the speed of light, the energy required becomes infinite, making it impossible for anything with mass to achieve. Light, being massless, is the only thing that can travel at this ultimate speed. But light doesn't just travel through space, it interacts with it. Massive objects like stars and black holes warp spacetime so dramatically that they bend light itself. This phenomenon, known as gravitational lensing, is like a cosmic magnifying glass, distorting and magnifying the light from distant galaxies. It's a vivid reminder that light doesn't exist in isolation. It's deeply tied to the energy and mass that shape the universe. Now, let's take this a step further with a thought experiment. Imagine you're on a spaceship traveling at 99% the speed of light. From your perspective, time would slow down and distances would shrink, a concept known as time dilation and length contraction. But here's the twist. No matter how fast you go, you'll never quite reach the speed of light. It's as if the universe has set an impenetrable barrier, a reminder that energy and spacetime are inextricably linked. But the story of light doesn't end with speed and bending. As the universe expands, light from distant galaxies stretches, shifting toward the red end of the spectrum, a phenomenon called redshift. This isn't just a quirk of physics, it's a direct consequence of cosmic energy shaping the universe. The expansion, driven by dark energy, stretches the wavelengths of light, carrying with it the story of the universe's growth over billions of years. What does all this mean for our understanding of the cosmos? It shows us that light isn't just a messenger, it's a participant in the cosmic dance, influenced by the energy that fills the universe. From the way it bends around massive objects to the way it stretches as space expands, light reveals the intricate interplay between energy, mass, and spacetime. And as we continue to explore these connections, we'll uncover even deeper insights into how cosmic energy shapes the universe, not just on the scale of light, but on the grand scale of galaxies, clusters, and the cosmic web itself. The speed of light may be a limit, but it's also a window into the profound forces that govern reality. The cosmic web isn't just a static backdrop for the universe. It's a dynamic, ever-changing network shaped and sustained by the invisible hand of cosmic energy. Picture a spider's web glistening with dew in the morning light. Each strand is connected, each intersection a hub of activity. Now imagine that web on a cosmic scale, stretching across billions of light years, with galaxies and clusters of dark matter strung along its threads like beads. This is the cosmic web, a vast, intricate structure that defines the large-scale organization of the universe. At the heart of this web lies gravitational potential energy, a force that binds galaxies together while also driving their movement. Think of it like a cosmic tug of war. On one side, gravity pulls galaxies toward each other, clustering them into dense nodes. On the other side, dark energy pushes the fabric of spacetime apart, stretching the web thinner over time. It's this delicate balance between attraction and repulsion that shapes the cosmic web, creating the filaments, voids, and nodes we observe today. But how does cosmic energy influence this process? The answer lies in the way energy flows through the web. As galaxies move along the filaments, they exchange gravitational energy, much like marbles rolling down the curves of a cosmic slide. This energy isn't just a byproduct, it's the driving force behind the web's evolution, determining where galaxies form, how they cluster, and even how they interact with one another. And here's where it gets even more fascinating. The cosmic web isn't just a map of galaxies, it's also a map of dark matter. This mysterious substance, invisible to telescopes, makes up most of the universe's mass. Its gravitational pull shapes the web, creating the deep gravitational wells that galaxies and clusters call home. Without dark matter, the cosmic web would look very different, less structured, less interconnected. Now let's zoom in on one of these nodes where galaxies cluster together in dense, vibrant hubs. These regions are like cosmic cities, bustling with activity as galaxies collide, merge, and give birth to new stars. The energy released during these collisions ripples through the web, influencing nearby galaxies and even shaping the voids between them. It's a reminder that the cosmic web isn't just a structure. It's a living, breathing network, constantly reshaped by the forces of cosmic energy. But the story of the cosmic web doesn't end here. Just as cosmic energy shapes the largest structures in the universe, it also influences the smallest scales of existence, a connection we'll explore next. From the vast filaments of the web to the subatomic particles that make up matter, cosmic energy is the thread that ties the universe together, weaving a tapestry of complexity and beauty that stretches from the grandest galaxies to the tiniest particles. So, the next time you gaze at the night sky, remember this: the stars and galaxies you see are part of a much larger story, one written in the language of energy and shaped by the forces that govern the cosmos. And as we continue to explore this story, we'll uncover even more ways that cosmic energy connects us to the very heart of the universe. Now, let's shrink our perspective down to the tiniest scales imaginable, the quantum realm, where the rules of the universe take on a bizarre and unpredictable twist. Here, cosmic energy reveals itself in ways that challenge our understanding of reality. In this microscopic world, particles pop in and out of existence, and the seemingly empty vacuum of space is anything but empty. It's a bubbling cauldron of activity, a place where cosmic energy manifests in its most mysterious and fundamental form. At the heart of this quantum chaos lies zero-point energy, the lowest possible energy state of a system. Even in a perfect vacuum where you'd expect nothingness, there's still a faint hum of energy. Picture a pot of water on the verge of boiling. Tiny bubbles form and burst, creating a constant, barely visible motion. Now replace the water with space itself, and the bubbles with particles and antiparticles spontaneously appearing and disappearing. This is the quantum vacuum, a seething sea of energy fluctuations that underlies everything in the universe. What's truly mind-blowing is that these quantum fluctuations aren't just theoretical, they have real, measurable effects. For instance, they're responsible for the Casimir effect, where two metal plates placed extremely close together in a vacuum experience an attractive force. It's as if the energy bubbling between them pushes the plates together, a subtle but undeniable sign of the quantum world's restless energy. But here's where it gets even more fascinating. These fluctuations might play a role in the universe's energy budget. Some scientists speculate that zero-point energy could contribute to dark energy, the mysterious force driving the accelerated expansion of the cosmos. If true, this would mean that the energy of the quantum vacuum isn't just a quirk of physics, it's a fundamental part of the universe's evolution, shaping its past, present, and future. Think of the quantum realm as the universe's engine room, where cosmic energy is constantly churning, fueling the cosmos on both the smallest and largest scales. From the tiniest particles to the vast expanse of space, this energy connects everything, weaving a tapestry of complexity that's as beautiful as it is mysterious. And as we peer deeper into this quantum cauldron, one question lingers. Could the energy of the quantum vacuum hold the key to understanding the origins of the universe itself? Some theories suggest that the Big Bang might have been sparked by a massive fluctuation in this energy, a cosmic ripple that set everything into motion. It's a tantalizing idea, one that blurs the line between the quantum and the cosmic, and it hints at a deeper unity between the smallest particles and the grandest structures in existence. So, the next time you think about the universe, remember this: even in the seeming stillness of space, cosmic energy is at work, pulsating in the quantum realm and shaping the cosmos in ways we're only beginning to understand. And as we continue to explore this mysterious energy, we may uncover even deeper truths about the universe and our place within it. Now, let's take a leap beyond the boundaries of our universe and into the realm of the multiverse, a mind-bending concept that suggests our cosmos might be just one of countless others. This brings us to our 17th revelation. Cosmic energy could be the key to understanding not just our universe, but the existence of multiple universes. What if the energy that shapes stars, galaxies, and even spacetime itself is also responsible for birthing entirely separate realities? Picture the multiverse as a cosmic foam, with each bubble representing a unique universe. These bubbles aren't static, they're constantly forming, merging, and sometimes even popping, driven by the same cosmic energy that fuels our own universe. This idea, known as the inflationary multiverse theory, suggests that during the rapid expansion of the early universe, a process called cosmic inflation pockets of spacetime could have broken away, forming their own self-contained realities. Each of these bubble universes might have its own laws of physics, its own stars, and even its own forms of life. But what role does cosmic energy play in this process? Think of it like this: just as a pot of boiling water creates bubbles on its surface, cosmic energy creates fluctuations in spacetime. In some cases, these fluctuations grow so large that they pinch off, forming new universes. It's a process driven by the same energy that shaped our universe during the Big Bang, but instead of creating one cosmos, it creates many. Here's where it gets even more intriguing. These bubble universes aren't just theoretical. Some scientists believe that evidence for their existence might be hidden in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Tiny anomalies in this radiation could be the fingerprints of other universes bumping into our own, leaving behind subtle imprints in the fabric of spacetime. But what does this mean for our understanding of reality? If the multiverse exists, it suggests that cosmic energy isn't just a force within our universe, it's a force that transcends it, shaping the very structure of existence on a scale we can barely comprehend. It's a reminder that our universe might be just one thread in a vast, intricate tapestry of realities, each one woven together by the same cosmic energy. And while the idea of a multiverse might seem like science fiction, it has profound implications for our own universe. If cosmic energy can create multiple universes, it might also hold the key to understanding the ultimate fate of our cosmos. Will it continue to expand indefinitely, driven by dark energy, or will it collapse back in on itself, ending in a cosmic crunch? As we explore these questions, one thing becomes clear. Cosmic energy is more than just a force, it's a storyteller, weaving together the past, present, and future of not just our universe, but potentially countless others. And as we continue to unravel its mysteries, we may find that the answers lie not just in the stars, but in the spaces between them, where the threads of reality are spun into existence. What if the universe, for all its grandeur and mystery, has an expiration date? This brings us to our 18th revelation. Cosmic energy isn't just shaping the universe today, it's also writing the final chapter of its story. From the fiery birth of stars to the silent expanse of space, cosmic energy holds the key to the ultimate fate of the cosmos. But how will it all end? Will the universe fade into cold, empty darkness, or will it collapse back in on itself in a cataclysmic finale? Let's start with one of the leading theories, the heat death of the universe. In this scenario, cosmic energy continues to push the universe apart, driven by the relentless expansion fueled by dark energy. Over trillions of years, stars will exhaust their fuel, galaxies will grow dim, and the universe will cool to a near-absolute zero. It's a slow, quiet end, a cosmic whisper rather than a bang. Imagine a room where the lights gradually dim until there's nothing left but darkness. This is the heat death, a fate where the universe becomes a vast, cold, and lifeless void. But not all scientists agree. Another possibility is the Big Crunch, a dramatic reversal of the universe's expansion. In this scenario, dark energy's repulsive force weakens over time, allowing gravity to take over. Galaxies, stars, and even spacetime itself would collapse inward, culminating in a fiery, high-energy implosion. Picture the universe as a cosmic hourglass, with all matter and energy funneling back into a single, infinitely dense point, a mirror image of the Big Bang. The debate between these two outcomes hinges on the behavior of dark energy. Will it continue to dominate, stretching the universe into an ever thinner fabric? Or will it fade, allowing gravity to reclaim its hold? Scientists are still searching for answers, using tools like the cosmic microwave background and observations of distant supernova to piece together the universe's trajectory. Here's where it gets even more fascinating. The fate of the universe isn't just a question of physics, it's a question of life itself. If the universe ends in heat death, life as we know it would eventually become impossible, as energy becomes too sparse to sustain complex systems. But if the Big Crunch occurs, the universe might collapse and potentially rebound, sparking a new cycle of creation. Could life emerge again in a new universe born from the ashes of the old? As we ponder these cosmic possibilities, one thing becomes clear. The story of the universe is deeply intertwined with the story of energy. From the smallest particles to the largest galaxies, cosmic energy shapes not just the present, but the future of existence itself. And while the ultimate fate of the universe remains uncertain, its journey is a testament to the incredible forces that govern reality. But the story of cosmic energy doesn't end with the fate of the universe. It also plays a vital role in the emergence of life, a connection that we'll explore next. From the energy of stars to the chemistry of planets, cosmic energy is the spark that makes life possible, and that's where our journey continues. Could the energy that fuels the stars and shapes galaxies also be the spark that ignited life itself? This brings us to our 19th revelation. cosmic energy might hold the key to one of the greatest mysteries of all: how life began on Earth. From the warmth of the sun to the invisible rain of cosmic rays, energy from the cosmos has been shaping our planet for billions of years, creating the conditions that made life possible. Let's start with the sun, the ultimate energy source for life on Earth. Its light doesn't just keep us warm and power photosynthesis, it also played a crucial role in the planet's early chemistry. Billions of years ago, when Earth was still a young, volatile world, the sun's ultraviolet radiation likely triggered chemical reactions in the planet's primordial soup. These reactions could have transformed simple molecules into more complex ones, laying the groundwork for the first organic compounds. But the sun isn't the only cosmic force at play. Cosmic rays, high-energy particles from distant supernova and other cosmic events also bombard our planet. While these rays might sound like something out of a sci-fi movie, they've been influencing Earth since its formation. Some scientists believe that cosmic rays could have provided the energy needed to break apart molecules in the atmosphere, creating the building blocks for life. It's as if the universe itself was sending down tiny sparks, jump-starting the chemistry of life. To put this idea to the test, scientists like Stanley Miller and Harold Urey conducted a groundbreaking experiment in the 1950s. They recreated Earth's early atmosphere in a lab, filling a glass flask with water, methane, ammonia, and hydrogen gases thought to be present on the young planet. Then they added an electric spark to simulate lightning, another source of energy. Within days, the experiment produced amino acids, the essential molecules that make up proteins and life as we know it. While the Miller-Urey experiment didn't recreate every detail of Earth's early conditions, it showed that energy, whether from lightning, sunlight, or cosmic rays, could indeed kickstart the chemistry of life. What's truly remarkable is that cosmic energy didn't just play a role in the origins of life, it continues to shape life today. The sun's energy powers every ecosystem on Earth, from the tiniest microbes to the tallest trees. Cosmic rays, meanwhile, still bombard our planet, subtly influencing everything from genetic mutations to cloud formation. Even the energy stored in fossil fuels, the remnants of ancient sunlight captured by plants millions of years ago, powers our modern world. So, the next time you feel the warmth of the sun on your skin or gaze up at the stars, remember this: the energy that fills the cosmos isn't just out there, it's here, woven into the very fabric of life. And as we continue to explore this connection, we may uncover even deeper truths about how the universe shaped not just the stars and galaxies, but the story of life itself. But the influence of cosmic energy doesn't stop at life's origins. It also plays a role in shaping the evolution of species, a topic we'll explore next as we dive into the intersection of cosmic forces and the diversity of life on Earth. What if the energy that powers the stars and shapes galaxies also plays a role in something far closer to home: your thoughts, your awareness, your very sense of self? This brings us to our 20th revelation. Cosmic energy might not just shape the universe around us, it could also be intertwined with human consciousness itself. It's a bold idea, one that bridges the gap between the vast cosmos and the inner workings of the mind, and it raises a profound question: could the universe itself be conscious? Let's start with the science of consciousness, one of the most elusive mysteries in all of biology and physics. While we still don't fully understand how the brain generates subjective experience, some researchers have proposed that quantum mechanics, the same physics that governs the behavior of particles and energy, might hold the key. One theory, known as quantum consciousness, suggests that cosmic energy, through quantum processes, could play a role in how the brain operates. Imagine your thoughts as tiny ripples in a vast cosmic ocean, influenced by the same energy that flows through stars and galaxies. At the heart of this idea is the concept of quantum coherence, where particles interact in highly organized, synchronized ways. In the brain, structures called microtubules, tiny protein fibers within neurons, might facilitate these quantum interactions. If true, this would mean that cosmic energy, in the form of quantum fluctuations, could influence how information is processed in the brain, potentially shaping our thoughts, decisions, and even our sense of self. But here's where it gets even more fascinating. If consciousness is linked to cosmic energy, could the universe itself possess some form of awareness? Some scientists and philosophers have speculated that the cosmos, on some level, might be conscious not in the way we think of human consciousness, but as a vast, interconnected network of energy and information. Think of it as a cosmic brain with galaxies and stars acting like neurons, exchanging energy and influencing one another across unimaginable distances. Of course, this is still a highly speculative idea, and many questions remain. How could something as intangible as cosmic energy give rise to something as complex as consciousness? And if the universe is conscious, what would that even mean for our understanding of reality? While we don't have all the answers, the connection between cosmic energy and consciousness opens up a new frontier in science, one that challenges our assumptions about the universe and our place within it. And as we ponder these questions, it's worth remembering that cosmic energy doesn't just influence the mind. It also shapes the behavior of celestial objects, from the smallest particles to the largest galaxies. This interconnectedness, where energy flows seamlessly from the quantum realm to the cosmic scale, reminds us that the universe is far more unified than we often realize. So, the next time you gaze at the stars or reflect on the nature of your own thoughts, consider this. The energy that fills the cosmos might also be the spark that lights the flame of consciousness, connecting us to the universe in ways we're only beginning to understand. And as we continue to explore this profound connection, we may uncover not just the secrets of the mind, but the deeper truths of existence itself. From the quiet hum of the quantum vacuum to the explosive power of supernova, cosmic energy takes on countless forms across the universe. But one of its most dramatic displays happens closer to home, on the surface of our own sun. This brings us to the 21st revelation. Cosmic energy doesn't just fuel the stars, it erupts in spectacular bursts known as solar flares, reshaping the space around us and reminding us of the sun's raw, untamed power. A solar flare is like the sun's version of a cosmic temper tantrum, a sudden, intense release of energy that can dwarf the combined output of 1 billion nuclear bombs. These eruptions occur when tangled magnetic fields on the sun's surface snap and reconnect, unleashing a torrent of energy in the form of light, radiation, and charged particles. The sheer scale of these events is almost beyond comprehension. In just minutes, a single flare can release enough energy to power the entire planet for thousands of years. But what happens when this energy reaches Earth? While our planet's magnetic field acts as a shield, deflecting most of the sun's fury, solar flares can still pack a punch. They interact with Earth's magnetosphere, creating dazzling auroras that light up the polar skies. These natural light shows, while beautiful, are just the visible tip of the iceberg. Solar flares can also disrupt satellites, knock out power grids, and interfere with communication systems. In an increasingly tech-dependent world, these disruptions are more than just an inconvenience. They're a reminder of how deeply connected we are to the sun's energy. To understand the potential impact, consider the Carrington event of 1859, the most powerful solar storm ever recorded. Named after the astronomer Richard Carrington, who observed the massive flare, this event sent a surge of charged particles racing toward Earth. Telegraph systems, the cutting-edge technology of the time, went haywire, with operators reporting sparks flying from their equipment and even setting papers on fire. If a similar event occurred today, the consequences could be catastrophic, potentially causing widespread blackouts and disrupting global communication networks for days or even weeks. What makes solar flares so fascinating isn't just their destructive potential, it's what they reveal about the sun's role in the cosmic energy network. The sun isn't just a passive ball of gas, it's a dynamic, ever-changing engine, constantly reshaping the space around it. From the smallest magnetic loops to the largest solar storms, the sun's energy is a driving force in the solar system, influencing everything from the weather on Earth to the behavior of distant planets. And while solar flares are a stunning example of cosmic energy in action, they're just one piece of the puzzle. From the gentle glow of starlight to the explosive power of gamma-ray bursts, the universe is filled with phenomena that showcase the incredible diversity of cosmic energy. Each one tells a story, a chapter in the grand narrative of the cosmos, and as we continue to explore these stories, we'll uncover even more ways that energy shapes the universe and our place within it. So, the next time you see the sun shining in the sky, remember this. It's not just a source of light and warmth, it's a cosmic powerhouse capable of unleashing energy on a scale that defies imagination. And as we look deeper into the sun's fiery heart, we may find that it holds the key to understanding not just our solar system, but the broader mysteries of the universe itself. While solar flares remind us of the sun's raw power, there's another cosmic phenomenon that dwarfs even the most intense solar eruptions: gamma-ray bursts. These fleeting but catastrophic events are like the universe's ultimate fireworks show, lighting up the cosmos with energy so immense it defies comprehension. In just a few seconds, a single gamma-ray burst can release more energy than the sun will emit over its entire 10 billion-year lifespan. It's a staggering display of cosmic power, one that leaves scientists in awe and raises profound questions about the forces behind these extraordinary explosions. So, what causes these bursts of unimaginable energy? Most gamma-ray bursts originate from the deaths of massive stars, events so violent they can outshine entire galaxies for a brief moment. When a star many times more massive than our Sun exhausts its fuel, its core collapses under its own gravity, forming a black hole or neutron star. As this happens, jets of energy are blasted outward at nearly the speed of light, creating the gamma-ray burst we observe. It's like a cosmic beacon, signaling the end of one star's life and the birth of something entirely new. But gamma-ray bursts aren't just one-time spectacles, they play a crucial role in the universe's evolution. The energy released during these events can travel across billions of light years, influencing the formation of galaxies and even the chemistry of distant worlds. Some scientists believe that gamma-ray bursts may have contributed to the conditions necessary for life on Earth, as their intense radiation could have triggered chemical reactions in the early solar system. It's a reminder that even the most destructive events in the cosmos can have far-reaching constructive effects. To put their energy into perspective, imagine the entire output of the sun concentrated into a single beam, narrower than the width of a pencil. That's the kind of intensity we're talking about with gamma-ray bursts. If one occurred within a few thousand light-years of Earth, the results could be catastrophic, stripping away our ozone layer and exposing the planet to harmful radiation. Fortunately, these events are rare and typically occur in distant galaxies, making them a breathtaking spectacle rather than a direct threat. What's truly fascinating is how gamma-ray bursts connect to another cosmic mystery: black holes. Many of these bursts are thought to result from the formation of black holes, as the collapsing star's immense energy is funneled into powerful jets. These jets, in turn, interact with the surrounding space, creating shockwaves and radiation that ripple across the cosmos. It's a vivid reminder that cosmic energy isn't just a force, it's a storyteller, weaving together the lives and deaths of stars in a grand, interconnected narrative. As we peer deeper into the mysteries of gamma-ray bursts, we're reminded of the universe's capacity for both destruction and creation. These events aren't just random explosions, they're part of a larger cosmic dance where energy flows from one form to another, shaping the universe in ways we're only beginning to understand. And as we continue to explore this dance, we'll uncover even more ways that cosmic energy connects the smallest particles to the largest structures in existence. Imagine a beacon so bright it outshines entire galaxies, a cosmic lighthouse piercing the darkness of space with unimaginable intensity. This is a quasar, one of the most luminous objects in the universe, powered by the immense energy of supermassive black holes. These celestial powerhouses don't just illuminate the cosmos, they shape it, influencing the birth and evolution of galaxies across billions of years. At the heart of every quasar lies a supermassive black hole, millions or even billions of times more massive than our Sun. But unlike their quieter counterparts, these black holes are far from dormant. They're surrounded by swirling disks of gas and dust, material drawn in by their immense gravity. As this matter spirals inward, it heats up to incredible temperatures, releasing vast amounts of energy in the form of light, X-rays, and other radiation. It's this process, known as accretion, that makes quasars so staggeringly bright. To put this into perspective, a single quasar can emit more energy than 1,000 Milky Way galaxies combined. Yet, despite their brilliance, quasars are incredibly distant, located billions of light-years away. This means that when we observe them, we're peering back in time, witnessing the universe in its youth. And what we're seeing is nothing short of extraordinary. Quasars aren't just cosmic oddities, they're key players in the story of galaxy formation. Here's how it works. As quasars release their energy, they create powerful jets and winds that blast outward, shaping the surrounding gas and dust. These outflows can trigger the collapse of gas clouds, sparking the birth of new stars and even entire galaxies. At the same time, they can also halt star formation by blowing away the raw materials needed to create stars. It's a delicate balance, one that quasars help regulate, acting as cosmic architects that influence the growth and evolution of galaxies. But quasars aren't just builders, they're also destroyers. The intense radiation they emit can strip away the atmospheres of nearby planets, making it difficult for life to take hold. Yet, in the grand scheme of the universe, this destructive power is part of a larger cycle of creation and transformation. The energy released by quasars doesn't just vanish, it spreads across the cosmos, seeding the universe with the raw materials needed for new stars, planets, and galaxies to form. What's truly remarkable is how quasars connect to the broader structure of the universe. They're often found at the centers of galaxy clusters, the largest structures in the cosmos, and their energy can influence the distribution of matter on a colossal scale. It's as if quasars are cosmic weavers, threading energy through the fabric of the universe and shaping its very architecture. As we continue to explore these dazzling objects, we're reminded of the profound role cosmic energy plays in the universe. From the tiniest particles to the largest galaxies, energy is the thread that ties everything together, driving the endless cycle of creation and transformation. And as we turn our attention to the universe's large-scale structure, we'll uncover even more ways that cosmic energy shapes the cosmos, weaving a tapestry of complexity and beauty that stretches across billions of light years. What if the universe is filled with something we can't see, a shadowy substance that shapes galaxies, bends light, and holds the cosmos together? This brings us to our 24th revelation, the enigmatic connection between cosmic energy and dark matter. Despite making up about 85% of the universe's mass, dark matter remains one of the greatest mysteries in science. Unlike the stars and planets we observe, dark matter doesn't emit, absorb, or reflect light. It's invisible, yet its gravitational influence is everywhere, shaping the universe in ways we're only beginning to understand. To grasp the scale of dark matter's impact, imagine a galaxy like our Milky Way. The stars within it are like glowing lanterns floating on an invisible sea. That sea is dark matter, a vast, unseen structure that provides the gravitational scaffolding for galaxies to form and grow. Without it, galaxies would fly apart, unable to hold their shape against the forces of cosmic expansion. It's as if dark matter is the universe's hidden architect, quietly building the framework for everything we see. But here's the question that keeps scientists up at night. What is dark matter made of? Is it a sea of exotic particles unlike anything we've ever detected? Could it be composed of tiny black holes formed in the earliest moments of the universe? Or is it something even stranger, defying our current understanding of physics? While we don't yet have the answers, one thing is clear. Dark matter's gravitational pull is real, measurable, and essential to the cosmos as we know it. To detect something that doesn't interact with light, scientists rely on its gravitational effects. For instance, when light from a distant galaxy passes near a massive object like a cluster of dark matter, it bends, a phenomenon known as gravitational lensing. This bending creates distorted or magnified images of the background galaxy, allowing astronomers to map the distribution of dark matter in the cluster. It's like using light as a cosmic flashlight, revealing the unseen structure of the universe. Now, let's consider how cosmic energy fits into this picture. While dark matter shapes the universe through gravity, cosmic energy, particularly dark energy, works in the opposite direction, driving the accelerated expansion of space. Together, these two forces create a delicate balance, shaping the large-scale structure of the cosmos. Dark matter pulls, dark energy pushes, and between them, they weave the intricate tapestry of the universe. But dark matter's influence doesn't stop at gravity. Some theories suggest that it might interact with cosmic energy in ways we don't yet understand. For example, could dark matter particles decay into energy, subtly influencing the behavior of light or even the expansion of the universe? Or might dark matter and cosmic energy be two sides of the same cosmic coin, interconnected in ways that challenge our current models of physics? These are questions that push the boundaries of science, inviting us to rethink our understanding of the universe. As we continue to explore the mysteries of dark matter, one thing is certain. It's a reminder of how much we still have to learn about the cosmos. From its invisible gravitational web to its potential connections with cosmic energy, dark matter is a key piece of the puzzle, one that could unlock new insights into the nature of reality itself. And as we turn our attention to the behavior of light, we'll uncover even more ways that cosmic energy shapes the universe, from the bending of starlight to the echoes of the Big Bang. The story of the cosmos is far from over, and with each new discovery, we're reminded of the incredible forces that connect us to the heart of the universe. Now, let's dive into a discovery that has revolutionized our understanding of the cosmos: gravitational waves. These ripples in spacetime are like cosmic echoes, carrying the energy of some of the most violent and energetic events in the universe. Imagine tossing a stone into a still pond. The ripples spread outward, distorting the surface in gentle, concentric waves. Gravitational waves are similar, except instead of water, they ripple through the very fabric of spacetime itself, carrying energy across unimaginable distances. So, what causes these spacetime ripples? They're born from cataclysmic events involving massive objects, like the collision of two black holes or the explosive death of a massive star. When these events occur, they release staggering amounts of energy, warping spacetime and sending gravitational waves racing outward at the speed of light. It's as if the universe itself is ringing like a bell, with each wave carrying the signature of the event that created it. Detecting these waves is no small feat. Gravitational waves are incredibly subtle, stretching and compressing spacetime by distances smaller than the width of an atom. To observe them, scientists use instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, which uses lasers and mirrors to measure these tiny distortions. The first direct detection of gravitational waves in 2015 was a landmark moment, confirming a prediction made by Einstein a century earlier and opening a new window into the universe. What makes gravitational waves so significant is the energy they carry. When two black holes merge, for example, they convert a portion of their mass into pure energy, radiating it outward as gravitational waves. In just a fraction of a second, these waves can release more energy than all the stars in the observable universe combined. It's a breathtaking reminder of the sheer power contained within cosmic events. But gravitational waves aren't just about energy, they're also messengers carrying information about the events that created them. By analyzing these waves, scientists can learn about the properties of black holes, neutron stars, and even the early universe. It's like listening to the whispers of the cosmos, uncovering secrets that were once hidden from view. As we explore the significance of gravitational waves, one thing becomes clear. They're not just ripples in space-time, they're a testament to the dynamic, ever-changing nature of the universe. And while they reveal the immense energy released by cosmic events, they also hint at something even larger, the role of cosmic energy in the universe's ongoing expansion. But that's a story for another time, as we continue to unravel the mysteries of the cosmos and the forces that shape it. What if the universe is expanding faster than we thought? And what does that mean for the future of everything we know? This brings us to our 26th revelation, cosmic energy and the Hubble constant, a number that holds the key to understanding the rate at which the universe is growing. Named after astronomer Edwin Hubble, who first observed the expansion of the universe, the Hubble constant is one of the most important and debated figures in cosmology. It's a measure of how quickly galaxies are moving away from each other, driven by the relentless push of cosmic energy. To visualize this, imagine baking a loaf of raisin bread. As the dough rises, the raisins move farther apart, just like galaxies drifting away from one another in an expanding universe. The Hubble constant tells us how fast this expansion is happening. But here's the catch: scientists don't all agree on the exact value of this constant. Some measurements based on observations of nearby galaxies suggest a faster expansion rate, while others, using distant light from the cosmic microwave background, point to a slower one. This discrepancy, known as the Hubble tension, has sparked intense debate in the scientific community. Could it be a sign that our understanding of cosmic energy is incomplete? Or might there be something fundamentally different about the universe's behavior now compared to its early stages? These questions aren't just academic. They could reshape our understanding of dark energy, the mysterious force driving the universe's accelerated expansion. What makes the Hubble constant so fascinating is how it connects the largest scales of the cosmos to the smallest. While it tells us about the expansion of galaxies billions of light years apart, it also hints at the behavior of particles and energy on the tiniest scales. Could the same cosmic energy that stretches the universe also influence the quantum realm, where particles flicker in and out of existence? As we grapple with these questions, one thing is clear: the Hubble constant isn't just a number, it's a window into the universe's past, present, and future. By understanding how cosmic energy drives the expansion of space, we're not just learning about the cosmos, we're uncovering the forces that shape reality itself. And as we turn our attention to the behavior of particles, we'll discover even more ways that cosmic energy connects the vast expanse of the universe to the smallest building blocks of existence. Imagine a particle so elusive that it can pass through an entire planet without ever stopping, a ghostly traveler that carries secrets from the farthest reaches of the cosmos. Meet the neutrino, one of the universe's most mysterious and abundant particles. Billions of them are streaming through your body right now, completely unnoticed. These nearly massless particles are cosmic messengers, carrying energy across unimaginable distances and playing a crucial role in some of the universe's most dramatic events. Neutrinos are born in the hearts of stars during nuclear reactions that power their fiery cores. They're also produced in massive quantities during supernova, the explosive deaths of massive stars. When a star collapses, it releases an incredible burst of energy, and neutrinos are among the first particles to escape, racing outward at nearly the speed of light. In fact, during a supernova, neutrinos carry away about 99% of the star's energy, leaving just a small fraction to create the dazzling light show we observe. What makes neutrinos so unique is their ability to travel vast distances without interacting with matter. Unlike light, which can be absorbed or scattered, neutrinos pass through almost everything: stars, planets, even entire galaxies, as if they weren't there. This ghostly behavior makes them incredibly difficult to detect, but it also makes them invaluable messengers. By studying neutrinos, scientists can peer into the hearts of stars and supernova, uncovering processes that would otherwise remain hidden. To better understand their role, think of neutrinos as cosmic postcards. Each one carries a snapshot of the environment where it was created, whether it's the intense heat and pressure inside a star or the chaotic aftermath of a supernova. By decoding these messages, researchers can piece together the story of how stars live, die, and shape the universe around them. But neutrinos don't just tell us about individual stars, they also hold clues about the early universe. In the first few seconds after the Big Bang, the cosmos was flooded with neutrinos, and some of these ancient particles are still traveling through space today. By studying them, scientists can gain insights into the conditions of the early universe, shedding light on how everything from galaxies to the cosmic web first formed. As we explore the role of neutrinos in cosmic energy, one thing becomes clear. These tiny particles are more than just passive travelers, they're active participants in the universe's grand story. From the fiery hearts of stars to the aftermath of cataclysmic explosions, neutrinos carry energy across the cosmos, connecting us to events that happened billions of years ago. And while neutrinos may be elusive, their impact is anything but. Just as they carry energy from distant stars, cosmic energy also powers the sun, the very source of life on Earth. But how does this energy make its way from the sun to our planet? That's the question we'll explore next as we dive into the incredible journey of solar energy and its role in shaping our world. Every second, deep within the heart of our sun, a cosmic miracle unfolds, one that has been powering life on Earth for billions of years. This is solar fusion, the process by which the sun transforms matter into cosmic energy, lighting up our solar system and sustaining the delicate balance of life. At its core, the sun is a colossal nuclear reactor, where temperatures soar to a staggering 15 million degrees Celsius, and pressures are so immense that hydrogen atoms are forced together in a fiery dance of creation. The journey begins with hydrogen, the simplest and most abundant element in the universe. Under the extreme conditions in the sun's core, hydrogen nuclei, each consisting of a single proton, collide with such force that they overcome their natural repulsion and fuse together. This fusion creates helium, a heavier element, and releases a burst of energy in the process. It's a bit like squeezing two droplets of water together until they merge, releasing a tiny spark in the process, except here, The spark is pure cosmic energy radiating outward in the form of light and heat. But the Sun's fusion process isn't just a single step. It's a chain reaction known as the proton-proton chain. First, two hydrogen nuclei fuse to form deuterium, a heavier isotope of hydrogen. Then deuterium combines with another hydrogen nucleus to create helium-3. Finally, two helium-3 nuclei collide, forming helium-4 and releasing two hydrogen nuclei back into the mix. Each step in this chain releases energy, contributing to the Sun's immense power output. To put this into perspective, the Sun converts about 4 million tons of matter into energy every second. That's the equivalent of detonating 1 billion nuclear bombs simultaneously. And yet, the Sun has been doing this for over 4.5 billion years with enough fuel to keep going for billions more. It's this relentless process of fusion that makes the Sun the ultimate source of cosmic energy, bathing our planet in warmth and light. But the Sun's energy doesn't just stay locked within its core. It travels outward layer by layer through the Sun's radiative and convective zones until it reaches the surface and bursts into space as sunlight. This journey can take tens of thousands of years, but once the energy escapes, it races toward Earth at the speed of light, arriving in just over 8 minutes. The impact of this energy on our planet is profound. It drives photosynthesis in plants, fuels weather systems, and even powers the technology we rely on every day. Without the Sun's fusion process, Earth would be a frozen, lifeless rock devoid of the energy that sustains us. Yet, the Sun's fusion isn't just a local phenomenon, it's part of a much larger story. The same process that powers our Sun also fuels stars across the universe, driving the evolution of galaxies and shaping the cosmic web. And as we turn our gaze to the broader cosmos, we'll uncover even more ways that cosmic energy weaves together the fabric of reality, connecting the smallest particles to the largest structures in existence. In the vast theater of the cosmos, galaxies aren't solitary actors, they're dancers, swirling and colliding in a cosmic ballet that shapes the very fabric of the universe. Galactic collisions are some of the most dramatic events in the cosmos, and they're fueled by an extraordinary release of cosmic energy. When two galaxies meet, their gravitational pull draws them together in a slow, inevitable embrace, setting off a chain reaction that can transform the structure of the universe itself. Imagine two dancers spinning toward each other, their movements growing faster and more chaotic as they collide. In a galactic collision, stars, gas, and dust are flung outward, creating dazzling arcs and streams of material that stretch across millions of light years. But this isn't just a random scattering of cosmic debris. It's a process rich with energy as gravitational forces compress gas clouds, triggering the birth of new stars. These stellar nurseries, glowing with the light of young, massive stars, are the universe's way of turning chaos into creation. The energy released during these collisions doesn't just spark star formation, it also reshapes the galaxies involved. Over billions of years, the two galaxies merge, their structures blending into a single, larger galaxy. This process, known as galactic cannibalism, is a testament to the transformative power of cosmic energy. The resulting galaxy might have a new shape, new stars, and even a new supermassive black hole at its center, formed from the merging of the original galaxy's black holes. But galactic collisions aren't just about destruction and rebirth, they're also a key driver of the universe's large-scale structure. When galaxies collide, their gravitational interactions can send shockwaves through the cosmic web, influencing the distribution of matter on a colossal scale. It's as if these collisions are cosmic catalysts, sparking changes that ripple outward, shaping the evolution of galaxy clusters and even the filaments of the cosmic web itself. Now consider this, the same cosmic energy that fuels galactic collisions also plays a pivotal role in the behavior of black holes. When galaxies merge, their supermassive black holes spiral toward each other, releasing gravitational waves and immense amounts of energy. These events are among the most powerful in the universe, and they offer a glimpse into the intricate interplay of cosmic forces. As we witness these cosmic dances, we're reminded that the universe is far from static. It's a dynamic, ever-changing tapestry, woven together by the threads of energy that flow through galaxies, stars, and black holes. And as we turn our attention to the role of black holes in this cosmic story, we'll uncover even more ways that energy shapes the universe, from the smallest particles to the largest structures in existence. At the heart of some of the most luminous objects in the universe lies a cosmic engine of unimaginable power, active galactic nuclei, or AN. These dazzling phenomena are fueled by supermassive black holes, which devour matter and release energy on a scale that defies comprehension. Picture a colossal whirlpool spinning at the center of a galaxy, surrounded by a glowing disk of gas and dust. As material spirals inward, it heats up to millions of degrees, unleashing torrents of radiation, jets of particles, and beams of light that can outshine the entire galaxy around it. This is the raw, untamed power of an active galactic nucleus, a testament to the incredible energy stored within the universe's most enigmatic objects. What makes AGNs so fascinating isn't just their brilliance, it's their role in shaping the galaxies they inhabit. These cosmic engines don't just sit quietly at the center of galaxies. They're dynamic, active forces that influence their surroundings in profound ways. The energy released by AGNs can heat up the surrounding gas, preventing it from collapsing to form new stars. In this way, AGNs act as cosmic regulators, controlling the rate at which galaxies grow and evolve. It's a delicate balance. Too much energy and star formation is stifled. Too little and galaxies might grow unchecked, their growth spiraling out of control. But the influence of AGNs extends far beyond their host galaxies. The jets of particles and radiation they emit can travel millions of light years, carving out vast bubbles in the intergalactic medium and influencing the formation of galaxy clusters. These jets are like cosmic blowtorches, sculpting the universe on the grandest scales and weaving energy into the fabric of the cosmic web. In this way, AGNs are not just local phenomena, they're key players in the universe's energy budget, shaping its structure and evolution over billions of years. Here's where it gets even more intriguing. The energy released by AGNs doesn't just disappear into the void. It interacts with the surrounding environment, heating gas, triggering star formation in distant regions, and even seeding the universe with heavy elements forged in the hearts of stars. It's a reminder that cosmic energy is never truly lost, it's constantly recycled, flowing from one form to another and shaping the cosmos in ways we're only beginning to understand. As we explore the role of active galactic nuclei, one thing becomes clear. These cosmic engines are more than just spectacular light shows. They're fundamental to the story of the universe. From regulating galaxy growth to shaping the large-scale structure of the cosmos, AGNs are a vivid reminder of how deeply interconnected the universe is, driven by the energy that flows through its every corner. And as we turn our gaze to the broader universe, we'll uncover even more ways that cosmic energy shapes the cosmos, from the smallest particles to the vast filaments of the cosmic web. The story of the universe is far from over, and with each new discovery, we're reminded of the incredible forces that connect us to the heart of existence. Picture a universe shrouded in darkness, a vast expanse of neutral hydrogen gas stretching across billions of light years. There were no stars, no galaxies, no light, just an endless void. But then, something extraordinary happened. A cosmic spark ignited, and the universe began to awaken. This pivotal moment, known as the cosmic dawn, marks the birth of the first stars and galaxies, a time when cosmic energy flooded the cosmos and forever transformed its fate. What sparked this cosmic awakening? The answer lies in the era of reionization, a transformative period that began roughly 100 million years after the Big Bang. Before this, the universe was opaque, filled with neutral hydrogen that absorbed light and kept the cosmos in shadow. But as the first stars and galaxies formed, their intense radiation began to ionize the surrounding hydrogen, stripping electrons from atoms and allowing light to travel freely. It was a cosmic renaissance, a time when the universe lit up with the glow of newborn stars and the energy they released. These first stars were unlike anything we see today. They were massive, hot, and short-lived, burning through their fuel in just a few million years before exploding as supernova. But in their brief lives, they released an incredible amount of cosmic energy, seeding the universe with heavier elements like carbon, oxygen, and iron, the building blocks of planets, moons, and even life itself. It's a process that continues to this day as stars forge the elements that shape the cosmos. The energy released during the cosmic dawn didn't just light up the universe, it also shaped its structure. As galaxies formed and grew, their gravitational pull drew in gas and dust, creating the first large-scale structures in the cosmos. These early galaxies acted as cosmic beacons, their light piercing the darkness and carving out the first threads of the cosmic web. Over billions of years, this web grew more intricate, connecting galaxies and clusters into the vast network we observe today. But the story of cosmic energy doesn't end with the cosmic dawn. The light from those first stars didn't just illuminate the universe, it also influenced the behavior of light itself. As photons traveled through the ionized gas, they interacted with electrons, scattering and spreading the energy across the cosmos. This process, known as Thomson's scattering, left its mark on the cosmic microwave background radiation, the faint afterglow of the Big Bang that we still observe today. It's a reminder that the energy of the cosmic dawn continues to echo through the universe, shaping its past, present, and future. As we peer back into this ancient era, we're reminded of the profound role cosmic energy plays in the universe's story. From the birth of the first stars to the formation of galaxies and the cosmic web, energy is the thread that ties everything together. And as we turn our attention to the behavior of light, we'll uncover even more ways that cosmic energy shapes the cosmos, weaving a tapestry of complexity and beauty that stretches across billions of light years. So, the next time you gaze at the night sky, remember this: the light you see is more than just a distant glow. It's the legacy of the cosmic dawn, a testament to the incredible power of cosmic energy. And as we continue to explore this ancient era, we may find that it holds the key to understanding not just our origins, but the very nature of reality itself. Now, let's travel back to a pivotal moment in the universe's infancy, a time when the cosmos underwent a transformation so profound it shaped everything we see today. This is the epoch of recombination, a cosmic milestone that occurred roughly 380,000 years after the Big Bang. Picture the universe as a dense, hot fog, filled with charged particles like protons and electrons, all buzzing with energy. In this early state, light couldn't travel far without being scattered, making the universe opaque, like a thick, glowing soup. But as the universe expanded and cooled, something extraordinary happened. The fog began to clear. This moment, known as recombination, marked the first time protons and electrons combined to form neutral hydrogen atoms. With this shift, the universe became transparent, allowing light to travel freely for the first time. Imagine it like a cosmic sunrise where the first rays of light pierce through the darkness, illuminating the cosmos. The energy released during this epoch didn't just light up the universe, it also left behind a faint glow, a snapshot of the early cosmos that we now call the cosmic microwave background radiation. Think of the cosmic microwave background as a cosmic photograph, a timeless image of the universe at the moment of recombination. This radiation, which we can still detect today, carries the imprint of the universe's early structure, revealing tiny fluctuations in density, the seeds of future galaxies and galaxy clusters. It's a remarkable reminder that the energy released during recombination didn't just vanish. It became a part of the universe's fabric, shaping its evolution over billions of years. But the significance of recombination goes even deeper. The moment light was set free marked the beginning of the universe's journey from a hot, dense state to the vast, structured cosmos we see today. It's like the universe took its first breath, exhaling energy into the void and setting the stage for the birth of stars, galaxies, and ultimately, life itself. And here's the fascinating part. The energy released during recombination didn't just illuminate the universe, it also played a role in its expansion. As the universe cooled and became transparent, the pressure of radiation decreased, allowing gravity to take over and pull matter together. This delicate interplay between energy and gravity continues to shape the cosmos, driving the formation of galaxies and the stretching of spacetime itself. As we reflect on this cosmic turning point, it's clear that the epoch of recombination wasn't just a moment in time. It was a foundational event, a cosmic pivot that set the stage for everything that followed. And as we turn our gaze to the universe's ongoing expansion, we'll uncover even more ways that cosmic energy continues to shape the cosmos, weaving a story that stretches from the first light to the farthest reaches of space. Now, let's rewind the cosmic clock even further, back to a time when the universe was just a fraction of a second old. This is the inflationary epoch, a brief but transformative period when the cosmos underwent an exponential growth spurt, stretching from the size of a subatomic particle to something far larger than the observable universe today. Picture a cosmic balloon inflating at an unimaginable speed, expanding faster than light itself. This wasn't just any expansion, it was a dramatic burst of cosmic energy that set the stage for everything we see in the universe today. During this epoch, cosmic energy specifically, a mysterious field called the inflaton field, drove this rapid expansion. The universe didn't just grow, it exploded outward, smoothing out irregularities and creating the remarkably uniform cosmos we observe. Think of it like stretching a wrinkled bedsheet. As the fabric expands, the creases and folds vanish, leaving behind a smooth, even surface. In the same way, inflation ironed out the universe, making it almost perfectly uniform in every direction. But why is this uniformity so important? It's the reason the universe looks so similar no matter where we look. Without inflation, the cosmos might have been a chaotic patchwork of hot and cold regions, making the formation of galaxies and stars far more difficult, if not impossible. Inflation gave the universe its blueprint, laying the groundwork for the cosmic web and the intricate structures we see today. Here's where it gets even more fascinating. The seeds of these structures, tiny quantum fluctuations in the inflaton field, were stretched to cosmic scales during inflation. These fluctuations, initially no larger than a single atom, became the building blocks of galaxies, galaxy clusters, and even the largest voids in the universe. It's as if the universe planted its own garden during this rapid expansion, scattering the seeds that would one day grow into the stars and galaxies we see today. But cosmic energy didn't just shape the universe on a grand scale, it also influenced the tiniest particles. During inflation, the same energy that drove the expansion also rippled through the quantum realm, creating the conditions for particles to form and interact in ways that would later define the laws of physics. This connection between the largest and smallest scales of existence is one of the most profound insights of modern cosmology, reminding us that cosmic energy is the thread that ties everything together. As we reflect on the inflationary epoch, one thing becomes clear. It wasn't just a moment in time, it was the foundation of the universe's story. From the smoothness of the cosmos to the seeds of galaxies, inflation set the stage for everything that followed. And as we explore the behavior of particles, we'll uncover even more ways that cosmic energy shapes the universe, bridging the gap between the quantum realm and the vast expanse of space. So, the next time you marvel at the night sky, remember this: the stars and galaxies you see are the legacy of an ancient burst of cosmic energy, a force that shaped the universe in its earliest moments and continues to influence its evolution today. And as we dig deeper into this story, we may find that the answers to some of the universe's greatest mysteries lie in the echoes of that primordial expansion. Now let's journey back to the very beginning, not just to the Big Bang, but to a time so early, so unimaginably brief, that our current understanding of physics begins to falter. This is the Planck era, a sliver of time so fleeting it lasted just 10 to the power of -43 seconds after the birth of the universe. To put that into perspective, if the entire history of the universe were condensed into a single year, the Planck era would occupy less than a trillionth of a second. Yet, despite its brevity, this infinitesimal moment holds the key to some of the most profound mysteries in science. During the Planck era, cosmic energy was at its most intense, packing the entire energy of the universe into a single, unimaginably dense point. Temperatures soared to over 10 to the power of 32 degrees Celsius, and the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single primal force. It's a time when the very fabric of spacetime was so warped, so chaotic, that our current laws of physics simply can't describe it. This raises a tantalizing question: what happened before the Planck era? Could there have been a before? The truth is, we don't know. Time itself, as we understand it, may not have existed. The Planck era marks the edge of our knowledge, a boundary where the familiar rules of physics dissolve into uncertainty. Some theories suggest that the universe may have emerged from a quantum fluctuation, a tiny ripple in the fabric of reality that gave birth to everything we see today. Others propose the existence of a multiverse, where our universe is just one of countless others, each with its own unique set of physical laws. Understanding the Planck era isn't just a matter of curiosity, it's a challenge that could redefine our understanding of reality. To peer into this primordial moment, scientists are working to develop a theory of quantum gravity, a framework that unites Einstein's theory of general relativity with quantum mechanics. Such a theory would allow us to explore the universe at its most fundamental level, revealing the secrets of cosmic energy in its purest form. But the implications of the Planck era don't stop at the birth of the universe. The intense energy of this epoch also shaped the behavior of black holes, those cosmic enigmas where gravity becomes so strong that even light can't escape. In fact, the conditions inside a black hole's singularity, a point of infinite density, may resemble those of the Planck era, offering a glimpse into the universe's earliest moments. As we reflect on this mysterious era, it's clear that cosmic energy isn't just a force that shapes the universe, it's the very essence of existence itself. From the Planck era to the sprawling cosmos we see today, energy is the thread that ties everything together, weaving a story that stretches from the smallest particles to the largest structures in the universe. And as we turn our attention to the role of cosmic energy in black holes, we'll uncover even more ways that this force shapes the cosmos, revealing the profound connections between the universe's beginning and its ongoing evolution. The story of the universe is far from over, and with each new discovery, we're reminded of the incredible forces that connect us to the heart of existence. What if the universe we see, its stars, galaxies, and even the very fabric of space-time isn't the full picture? What if everything we perceive is just a projection, a cosmic hologram encoded on the boundary of reality itself? This is the essence of the holographic principle, a mind-bending idea that suggests cosmic energy, and perhaps all of existence, can be described as information stored on the universe's outer edge. Imagine a movie projected onto a screen. The images you see aren't truly three-dimensional, but they appear that way because of how light and information are arranged. In the same way, the holographic principle proposes that our three-dimensional universe might just be a projection of information encoded on a two-dimensional surface. At its core, this principle challenges our understanding of space, time, and energy. Instead of thinking of the universe as a vast, three-dimensional expanse filled with matter and energy, the holographic principle suggests that all of this complexity could be reduced to data stored on a surface like the event horizon of a black hole or the boundary of the observable universe. It's as if the universe is a cosmic hard drive with every star, planet, and atom encoded as bits of information. This idea isn't just theoretical, it has roots in the study of black holes. When matter falls into a black hole, it doesn't just vanish. Its information is thought to be preserved on the event horizon, the point of no return. Physicists like Leonard Susskind and Gerard T. Hooft have extended this concept to the entire universe, suggesting that all physical phenomena, from the motion of planets to the glow of stars, might be encoded in a similar way. But what does this mean for cosmic energy? If the universe is a hologram, then energy itself might be a kind of encoded information, a pattern on the cosmic screen. This idea has profound implications for our understanding of reality. It suggests that energy isn't just a force within the universe, it's a fundamental aspect of how the universe stores and processes information. Here's where it gets even more intriguing. The holographic principle could help resolve one of the biggest puzzles in physics, the relationship between quantum mechanics and gravity. While quantum mechanics describes the behavior of particles on the smallest scales, gravity governs the largest structures in the cosmos. The holographic principle offers a way to bridge these two worlds, suggesting that the universe's energy and structure might be unified on a deeper, informational level. Think of it like this: if the universe is a hologram, then cosmic energy isn't just something that flows through space. It's the language the universe uses to express itself. From the tiniest particles to the largest galaxies, everything we see and experience might be a projection of this energy, a cosmic code written on the boundary of reality. As we explore the holographic principle, one thing becomes clear. It's a reminder of how interconnected the universe truly is. The same energy that shapes galaxies and powers stars might also be the key to understanding the fundamental nature of reality itself. And as we turn our attention to the universe's large-scale structure, we'll uncover even more ways that cosmic energy weaves together the fabric of existence, connecting the smallest particles to the vast expanse of the cosmos. So, the next time you gaze at the stars, consider this. The light you see might be more than just a distant glow. It could be part of a cosmic projection, a holographic masterpiece written in the language of energy and information. And as we continue to decode this universal code, we may find that the answers to some of the universe's greatest mysteries lie not in the stars themselves, but in the patterns they leave behind. Why does time only move forward? It's a question that seems simple at first, but when you dig deeper, it reveals one of the most profound mysteries of the universe, the arrow of time. Unlike space, which we can move through in any direction, time flows in one direction only, from the past to the future. And at the heart of this phenomenon lies cosmic energy, shaping not just the universe's structure, but also the very nature of time itself. To understand why time moves forward, we need to talk about entropy, a concept that describes the tendency of systems to move from order to disorder. Imagine a deck of cards perfectly sorted by suit and number. Shuffle it, and the order breaks down, increasing the deck's entropy. In the same way, the universe is constantly moving toward higher entropy, a process driven by cosmic energy. From the moment of the Big Bang, the universe has been expanding and cooling, creating more opportunities for energy to spread out and for systems to become less organized. This increase in entropy is what gives time its direction. It's the reason you can scramble an egg but never unscramble it. Now, let's connect this to the universe's expansion. As space stretches, driven by dark energy, it creates more room for entropy to increase. Think of it like blowing up a balloon. As it expands, the air molecules inside have more space to move around, increasing the system's disorder. In the same way, the universe's expansion provides the stage for entropy to rise, ensuring that time moves forward in an unbroken flow. But here's where it gets even more fascinating. The arrow of time isn't just a cosmic phenomenon, it's also deeply connected to the behavior of particles. At the quantum level, particles interact in ways that respect the direction of time, even if the underlying laws of physics are time-symmetric. This means that while particles can theoretically move backward in time, the overall flow of the universe, shaped by entropy and cosmic energy, keeps time moving forward. It's as if the universe has a built-in clock ticking in sync with the expansion of space and the increase of entropy. So, what does this mean for us? It suggests that the arrow of time isn't just an abstract concept, it's a fundamental part of reality, woven into the fabric of the cosmos by the interplay of energy, entropy, and expansion. And as we explore this connection, we're reminded that the universe isn't just a collection of objects in space, it's a dynamic, ever-evolving system, shaped by the forces that govern time itself. But the story doesn't end here. Just as cosmic energy influences the arrow of time, it also shapes the behavior of particles, from the tiniest quantum fluctuations to the largest structures in the cosmos. And that's where our journey continues next, as we uncover even more ways that energy connects the smallest scales to the vast expanse of the universe. At first glance, space appears to be a vast, empty void, a silent expanse where nothing exists. But what if that emptiness is an illusion? What if the vacuum of space is actually teeming with energy, a hidden force that shapes the universe in ways we're only beginning to understand? This brings us to our 37th revelation. Cosmic energy isn't just present in stars and galaxies, it fills the vacuum of space itself, driving the universe's expansion and revealing a deeper layer of reality. To grasp this idea, think of the vacuum of space not as an empty void, but as a cosmic sea, a shimmering, invisible ocean filled with energy. This energy, known as vacuum energy, is a fundamental property of space itself. Even in the absence of matter, particles, or light, the vacuum hums with activity. It's like a calm pond on a windless day where the surface looks still, but beneath it, tiny ripples and currents are constantly moving. In the same way, the vacuum of space is alive with energy fluctuations, a phenomenon predicted by quantum mechanics and confirmed by observations of the universe's behavior. But how does this energy influence the cosmos? One of its most profound effects is its role in the universe's expansion. According to Einstein's theory of general relativity, vacuum energy exerts a kind of pressure on spacetime, pushing galaxies apart and accelerating the universe's growth. This is where dark energy, the mysterious force driving the universe's expansion, comes into play. Many scientists believe that vacuum energy and dark energy are one and the same, a cosmic force embedded in the fabric of space itself. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon expands, the dots move farther apart. Now, replace the balloon with the universe and the dots with galaxies. Vacuum energy is like the air filling the balloon, stretching the fabric of spacetime and causing the galaxies to drift apart. It's a process that's been happening since the Big Bang, and it shows no signs of slowing down. What makes vacuum energy even more fascinating is its connection to quantum fluctuations. In the quantum realm, particles and antiparticles constantly pop in and out of existence, creating a seething, bubbling sea of energy. These fluctuations aren't just random noise, they're the universe's way of saying that even in nothingness there's potential. It's as if the vacuum of space is a cosmic reservoir, storing energy that can influence everything from the behavior of particles to the motion of galaxies. And here's the kicker, this energy isn't just out there, it's all around us. The same vacuum energy that stretches the universe also permeates every cubic inch of space, including the room you're in right now. While its effects are too subtle to notice on small scales, its cumulative impact on the cosmos is immense, shaping the universe's past, present, and future. As we explore the mysteries of vacuum energy, one thing becomes clear. The universe is far more dynamic and interconnected than we often realize. From the tiniest quantum fluctuations to the vast expanse of space, cosmic energy is the thread that ties everything together, driving the endless cycle of creation and transformation. And as we turn our attention to the Sun, we'll uncover even more ways that this energy shapes the cosmos, powering the very heart of our solar system and beyond. So the next time you gaze at the night sky, remember this: the stars and galaxies you see are floating on a cosmic sea, a hidden ocean of energy that fills the vacuum of space and drives the universe's endless dance. And as we continue to explore this energy, we may find that it holds the key to understanding not just the cosmos, but the very nature of reality itself. Now let's dive into a phenomenon that reveals the hidden energy lurking in the vacuum of space, a force so subtle yet so profound that it challenges our understanding of reality itself. This is the Casimir effect, a striking demonstration of how cosmic energy manifests even in the apparent emptiness of the universe. To grasp this concept, imagine two uncharged metal plates placed incredibly close together in a perfect vacuum. At first glance, you'd expect nothing to happen. After all, there's no obvious force acting on them. But here's where it gets fascinating. The plates are inexplicably drawn toward each other, as if pushed by an invisible hand. This is the Casimir effect in action, a phenomenon that proves the vacuum of space is anything but empty. So, what's really going on here? The answer lies in the quantum realm, where particles and antiparticles constantly flicker in and out of existence. In the space between the plates, only certain wavelengths of these quantum fluctuations can fit, creating a kind of energy imbalance. Outside the plates, however, fluctuations of all wavelengths are possible. This imbalance creates a pressure difference, pushing the plates together. It's as if the vacuum itself is alive, exerting a force that defies classical physics. The Casimir effect isn't just a curious quirk of quantum mechanics, it's a window into the nature of cosmic energy. It shows us that even in the absence of matter, space is teeming with energy, a seething, dynamic force that shapes the behavior of particles and, by extension, the universe itself. This energy, often called zero-point energy, is the lowest possible energy state of a system, and it's present everywhere, from the vast voids between galaxies to the tiniest gaps between atoms. But the implications of the Casimir effect go even deeper. It raises profound questions about the nature of reality. If the vacuum of space contains this much energy, could we one day harness it? Could it be the key to unlocking new technologies or even understanding the origins of the universe? While these questions remain open, the Casimir effect reminds us that the universe is far more complex and interconnected than we often realize. Now, consider this. Just as cosmic energy influences the tiny space between two plates, it also shapes the vast structures of the cosmos. The same quantum fluctuations that drive the Casimir effect may play a role in the formation of galaxies, the behavior of black holes, and even the expansion of the universe. It's a vivid reminder that the forces at work in the quantum realm are intimately connected to the grand tapestry of the cosmos. As we reflect on the Casimir effect, one thing becomes clear. The vacuum of space isn't just a backdrop for stars and galaxies, it's an active participant in the universe's story, a hidden reservoir of energy that shapes everything from the smallest particles to the largest structures. And as we explore this connection further, we'll uncover even more ways that cosmic energy weaves together the fabric of reality, bridging the gap between the quantum and the cosmic. So, the next time you think about the empty space around you, remember this: it's not truly empty. It's a dynamic, energy-filled realm where the forces of the universe are constantly at work, shaping the cosmos in ways we're only beginning to understand. And as we turn our attention to the behavior of galaxies, we'll see how this hidden energy continues to influence the universe on the grandest scales. Imagine a universe where even in complete stillness, there's an underlying hum of activity, a kind of cosmic background noise that never fades. This isn't just a metaphor, it's the reality of the zero-point field, the lowest possible energy state of a quantum system. Even in a perfect vacuum where you'd expect nothingness, this field buzzes with energy, a subtle but undeniable force that permeates every corner of the cosmos. But what exactly is this zero-point field, and why does it matter? At its core, the zero-point field is a consequence of quantum mechanics, which tells us that particles can never truly be at rest. Instead, they're constantly jittering, vibrating at the smallest scales, creating a faint but persistent energy that fills the vacuum of space. This energy isn't just theoretical, it's been observed in phenomena like the Casimir effect, where the zero-point field creates measurable forces between objects. It's as if the universe itself has a baseline energy, a kind of cosmic heartbeat that never stops. But the zero-point field isn't just a quirk of quantum mechanics. It plays a crucial role in the universe's energy budget. Some scientists speculate that this energy could contribute to dark energy, the mysterious force driving the accelerated expansion of the cosmos. If true, it would mean that the zero-point field isn't just a background hum, it's a fundamental force shaping the universe on the grandest scales. Here's a thought to ponder: could the universe itself be a quantum fluctuation in the zero-point field? Imagine the cosmos as a ripple in this vast, energy-filled sea, a tiny bubble that grew into the intricate web of galaxies and stars we see today. It's a bold idea, one that blurs the line between the quantum realm and the cosmic scale, suggesting that even the largest structures in existence might have their roots in the tiniest fluctuations of energy. As we explore the zero-point field, one thing becomes clear. It's a reminder of how deeply interconnected the universe truly is. From the smallest particles to the largest galaxies, energy flows seamlessly, connecting the quantum realm to the cosmic expanse. And as we turn our attention to the universe's large-scale structure, we'll see how this energy continues to shape the cosmos, weaving a tapestry of complexity and beauty that stretches across billions of light years. So, the next time you think about the universe, remember this: even in the quietest corners of space, there's a hidden energy at work, a force that connects the smallest particles to the grandest galaxies. And as we continue to unravel its mysteries, we may find that the zero-point field holds the key to understanding not just the cosmos, but the very nature of reality itself. What if the universe wasn't just a random collection of galaxies and stars, but a finely tuned system designed with life in mind? This brings us to our 40th revelation, the connection between cosmic energy and the anthropic principle. At its core, the anthropic principle suggests that the universe's fundamental laws and constants, like the strength of gravity or the speed of light, are precisely calibrated to allow life to exist. It's as if the cosmos hit the jackpot in a cosmic lottery, with every number aligning perfectly to create the conditions necessary for planets, stars, and ultimately living beings like us. To grasp this idea, imagine you're holding a lottery ticket with a 1 in a trillion chance of winning. Now, imagine that winning ticket isn't just a stroke of luck, it's the universe itself. The precise balance of cosmic energy, from the strength of the forces that hold atoms together to the expansion rate of space, is so finely tuned that even a slight variation would make life impossible. For example, if the energy released during the Big Bang had been just a fraction stronger, the universe would have expanded too quickly for galaxies to form. If it had been weaker, gravity would have pulled everything back into a cosmic collapse long before stars could ignite. This fine-tuning has led some scientists and philosophers to propose that the universe isn't just a random accident. It's a system where cosmic energy is calibrated to allow life to emerge. It's a profound idea, one that raises questions about the nature of reality and our place within it. Are we the result of a cosmic coincidence, or is there something deeper at play? The anthropic principle doesn't provide a definitive answer, but it invites us to consider the possibility that the universe is more than just a chaotic expanse. It's a stage set for life. Now, let's take this a step further. If the universe is fine-tuned for life, what does that mean for the behavior of particles? Just as cosmic energy shapes the large-scale structure of the cosmos, it also influences the smallest building blocks of matter. From the way electrons orbit atoms to the interactions between quarks, cosmic energy plays a role in defining the rules that govern the quantum realm. It's a reminder that the same forces that allow galaxies to form also make life possible, connecting the vast expanse of the universe to the tiniest particles that make up our world. As we explore the anthropic principle, one thing becomes clear. The universe is a place of incredible balance where cosmic energy weaves together the largest structures and the smallest particles in a delicate, interconnected dance. And as we turn our attention to the behavior of these particles, we'll uncover even more ways that energy shapes the cosmos, revealing the profound connections between the universe's design and the emergence of life itself. So, the next time you look up at the stars, remember this: the universe isn't just a random collection of matter and energy, it's a finely tuned system, one that allows life to exist and thrive. And as we continue to explore this remarkable balance, we may find that the answers to some of the universe's greatest mysteries lie not just in the stars, but in the very fabric of reality itself. Now let's zoom in on one of the most precise numbers in the universe, a number so finely tuned that even the slightest change would make life as we know it impossible. This is the fine structure constant, a fundamental physical constant that governs the strength of electromagnetic interactions. Think of it as a cosmic dial, carefully calibrated to allow atoms to form, light to shine, and chemistry to happen. If this constant were even a fraction larger or smaller, the universe would be a very different place. Stars might not burn, atoms might not bond, and life itself might never have emerged. The fine structure constant, often represented by the symbol alpha, is a dimensionless number that combines several fundamental constants: the charge of an electron, the speed of light, and Planck's constant. Together, these values determine how strongly charged particles, like electrons and protons, interact with each other and with light. It's like the universe's recipe for electromagnetism, dictating everything from the glow of a light bulb to the chemical reactions that power your body. What makes this constant so fascinating is its precision. For decades, scientists have measured alpha with incredible accuracy, and it always comes out to approximately 1/137. But here's the kicker: if this number were even slightly different, the universe as we know it wouldn't exist. If alpha were larger, atoms would hold their electrons more tightly, making chemical reactions impossible. If it were smaller, atoms would fall apart, unable to form the stable structures that make up molecules and matter. It's as if the universe hit a cosmic bullseye, with alpha perfectly balanced to allow complexity and life to emerge. This raises a profound question: why is the universe so finely tuned? Is it a coincidence, or is there something deeper at play? Some scientists suggest that the fine structure constant might be connected to cosmic energy, the same force that shapes stars, galaxies, and even the fabric of spacetime. Could the energy that fills the cosmos also influence the fundamental constants that define reality? It's a tantalizing idea, one that blurs the line between physics and philosophy, inviting us to rethink our understanding of the universe. But the story doesn't end with alpha. This constant also plays a crucial role in powering the sun, the ultimate source of cosmic energy in our solar system. The same electromagnetic interactions governed by the fine structure constant drive the fusion reactions that light up the sun, transforming hydrogen into helium and releasing the energy that sustains life on Earth. Without this delicate balance, the sun wouldn't shine, and the intricate web of life we see around us wouldn't exist. As we reflect on the fine structure constant, one thing becomes clear: it's a reminder of how deeply interconnected the universe truly is. From the tiniest particles to the largest stars, cosmic energy weaves together the fabric of reality, shaping the laws that govern existence. And as we continue to explore this intricate balance, we may uncover even more ways that energy connects the smallest scales to the vast expanse of the cosmos. So, the next time you marvel at the stars or flip on a light switch, remember this: the same forces that power the sun and light up your world are governed by a cosmic constant so precise, it's as if the universe itself is finely tuned for life. And as we turn our attention to the sun's fiery heart, we'll see how this energy continues to shape the cosmos, driving the endless cycle of creation and transformation. Imagine trying to measure the distance between two cities using nothing but a single ruler. Now, picture doing the same across billions of light-years of space. Sounds impossible, right? Yet, this is exactly what astronomers do with the cosmic distance ladder, a series of techniques that rely on cosmic energy to map the vast expanse of the universe. This ladder isn't just a tool, it's a testament to how energy connects us to the farthest reaches of the cosmos, allowing us to measure distances that defy imagination. At the heart of this cosmic measuring system are objects called standard candles, celestial beacons whose brightness is so consistent that they can be used to calculate distances. One of the most famous standard candles is the Type Ia supernova, a cataclysmic explosion of a white dwarf star. These supernovas shine with a predictable brightness, making them ideal markers for gauging distances across the universe. When astronomers detect a Type Ia supernova, they know its intrinsic brightness, and by comparing it to how dim it appears from Earth, they can calculate how far away it is. It's like seeing a lighthouse from a distance. The dimmer it looks, the farther away it must be. But supernovae aren't the only tools in the cosmic distance ladder. Another crucial rung is the Cepheid variable star. These stars pulsate in a regular rhythm, and their brightness changes in sync with their pulsations. The longer the pulsation period, the brighter the star shines. By measuring the period and apparent brightness of a Cepheid, astronomers can determine its distance. It's as if these stars are cosmic metronomes, ticking away in space and giving us a way to measure the vast distances between galaxies. Now, let's step back and think about what makes these measurements possible: cosmic energy. The light emitted by supernova and Cepheid variables is a form of energy traveling across space and time to reach us. Without the precise energy signatures of these objects, the cosmic distance ladder wouldn't work. It's a stunning reminder that energy isn't just a force, it's a language, one that allows us to decode the universe's secrets. But the cosmic distance ladder isn't just about measuring space, it's also about understanding the behavior of galaxies. By mapping the distances between galaxies, astronomers can study how they cluster, move, and evolve over time. And as we'll see next, these movements are deeply influenced by the same cosmic energy that powers stars, lights up supernova, and shapes the very fabric of the universe. So the next time you gaze at the night sky, remember this: the stars and galaxies you see aren't just points of light, they're part of a vast, interconnected network, one that we're only beginning to map. And as we climb the cosmic distance ladder, we're not just measuring space, we're uncovering the story of the universe itself. Now, let's step back and take in the universe on its grandest scale, a vast, intricate web of galaxies, clusters, and voids that stretch across billions of light years. This is the large-scale structure of the universe, a cosmic tapestry woven together by the invisible threads of cosmic energy. Picture it like a colossal spider's web, shimmering with galaxies at its intersections and vast, empty spaces in between. Each strand of this web is shaped by the interplay of dark matter, dark energy, and the gravitational forces that bind the cosmos together. At the heart of this structure lies dark matter, the universe's unseen architect. Imagine it as the scaffolding that holds galaxies in place, creating the deep gravitational wells where galaxies cluster together. Without dark matter's gravitational pull, galaxies would drift apart, unable to form the dense clusters and filaments we observe. It's like the invisible glue that keeps the cosmic web intact, ensuring that galaxies align along its threads like beads on a string. But dark matter isn't the only force at work. Dark energy, the mysterious force driving the universe's accelerated expansion, stretches this cosmic web, pulling galaxies apart and creating the vast voids between them. It's as if the universe is a balloon being steadily inflated, with dark energy acting as the air inside, pushing the galaxies farther and farther apart. These voids, seemingly empty, are actually regions where dark energy's influence is most pronounced, shaping the universe's overall structure. Together, dark matter and dark energy create a delicate balance, a cosmic tug-of-war between attraction and repulsion. Dark matter pulls galaxies together, while dark energy pushes them apart, creating the intricate patterns we see in the large-scale structure. It's a dance of forces that has been playing out since the universe's earliest moments, shaping everything from the smallest clusters to the largest filaments of the cosmic web. Now consider this: the same energy that shapes these colossal structures also influences the behavior of particles on the smallest scales. Just as dark matter and dark energy sculpt the universe's large-scale structure, cosmic energy weaves its way into the quantum realm, where particles flicker in and out of existence, driven by the same forces that govern the cosmos. It's a vivid reminder that the universe is deeply interconnected, from the vast expanse of space to the tiniest particles that make up matter. As we explore the large-scale structure of the universe, one thing becomes clear: cosmic energy isn't just a force, it's a storyteller, weaving together the past, present, and future of the cosmos. And as we turn our attention to the quantum realm, we'll uncover even more ways that this energy shapes the universe, revealing the profound connections between the largest structures and the smallest particles. So, the next time you gaze at the night sky, remember this: the galaxies and voids you see are part of a vast, interconnected network, one shaped by the invisible forces of cosmic energy. And as we continue to unravel this cosmic tapestry, we may find that the answers to some of the universe's greatest mysteries lie in the delicate balance between attraction and repulsion, creation and destruction, and the forces that bind the cosmos together. What if the universe left behind a map of its earliest moments, a blueprint that reveals how cosmic energy shaped everything we see today? This brings us to our 44th revelation, the cosmic microwave background anisotropies, tiny fluctuations in the oldest light in the universe that hold the secrets of its birth. Imagine looking at a photograph from the first moments of your life, capturing the raw energy and potential of your existence. The cosmic microwave background, or CMB, is the universe's version of that photograph, a snapshot of its infancy frozen in time. Discovered in 1965, the CMB is the afterglow of the Big Bang, a faint glow that fills the cosmos and carries the echoes of the universe's earliest moments. But this glow isn't perfectly uniform. If you look closely, you'll notice tiny variations in temperature fluctuations so small they're measured in millionths of a degree. These anisotropies, as they're called, might seem insignificant, but they're anything but. They're the fingerprints of cosmic energy, the seeds of all the structures we see in the universe today. So, what do these fluctuations tell us about the Big Bang? Think of them as ripples on the surface of a cosmic pond. In the early universe, quantum fluctuations, tiny, random variations in energy created these ripples. As the universe expanded, these ripples were stretched across vast distances, becoming the seeds for galaxies, galaxy clusters, and even the cosmic web itself. Without these tiny fluctuations, the universe might have remained a featureless void, devoid of the complexity and beauty we observe today. But the story doesn't end there. These anisotropies also reveal the universe's composition, including the mysterious dark energy that's driving its accelerated expansion. By studying the patterns in the CMB, scientists have pieced together a detailed picture of the early cosmos, confirming that dark energy makes up about 68% of the universe's total energy. It's a stunning reminder that the forces shaping the universe today were already at work in its earliest moments. Here's where it gets even more fascinating. The CMB isn't just a historical curiosity, it's a living testament to the universe's ongoing story. The energy that created these fluctuations continues to shape the cosmos, from the birth of stars to the clustering of galaxies. It's as if the universe left behind a cosmic treasure map, guiding us to uncover the forces that shaped its past and continue to influence its future. As we reflect on the cosmic microwave background, one thing becomes clear: the universe is far more interconnected than we often realize. From the tiniest fluctuations in energy to the largest structures in existence, cosmic energy weaves together the fabric of reality, connecting the past to the present and shaping the cosmos in ways we're only beginning to understand. And as we turn our attention to the Sun, the ultimate source of cosmic energy in our solar system, we'll see how this energy continues to shape the universe, driving the endless cycle of creation and transformation. The story of the cosmos is far from over, and with each new discovery, we're reminded of the incredible forces that connect us to the heart of existence. Let's zoom in on a cosmic phenomenon that reveals how energy interacts with some of the largest structures in the universe, a process known as the Sunyaev-Zeldovich effect. Picture a galaxy cluster, a massive gathering of hundreds or even thousands of galaxies bound together by gravity. Now, imagine this cluster isn't just sitting idly in space, it's surrounded by a hot, swirling sea of gas, heated to millions of degrees. This gas, while invisible to the naked eye, leaves a distinct mark on the cosmic microwave background radiation, the afterglow of the Big Bang. That mark is the Sunyaev-Zeldovich effect, and it's like a cosmic fingerprint, revealing the hidden energy within these colossal structures. Here's how it works. As the cosmic microwave background radiation travels through space, it occasionally passes through these galaxy clusters. When it does, the hot gas within the cluster scatters the photons, the particles of light, in the radiation, giving them a tiny boost in energy. This scattering distorts the radiation signature, creating a subtle but detectable imprint. To astronomers, this distortion is a treasure trove of information. It tells us not only about the gas within the cluster, but also about the cluster's mass, temperature, and even its distance from Earth. Think of it like this. If the cosmic microwave background is a pristine canvas, the Sunyaev-Zeldovich effect is the brushstroke that reveals the galaxy cluster's presence. It's a powerful tool for mapping the universe's large-scale structure, allowing scientists to trace the distribution of galaxy clusters across billions of light years. This mapping, in turn, helps us understand how dark matter and dark energy shape the cosmos, guiding the formation and evolution of these massive structures. But the Sunyaev-Zeldovich effect isn't just a tool for mapping, it's also a window into the universe's energy dynamics. The hot gas in galaxy clusters is a reservoir of cosmic energy, heated by the gravitational collapse of matter and the shocks from colliding galaxies. By studying this effect, scientists can measure how energy flows through these clusters, influencing everything from star formation to the behavior of supermassive black holes at their centers. Speaking of black holes, the interplay between cosmic energy and these enigmatic objects is equally fascinating. Just as the Sunyaev-Zeldovich effect reveals the energy within galaxy clusters, black holes also leave their own energetic fingerprints on the universe. From their intense gravitational pull to the jets of particles they spew into space, black holes are cosmic powerhouses, shaping their surroundings in ways we're only beginning to understand. As we explore these connections, one thing becomes clear. Cosmic energy isn't just a passive force, it's an active participant in the universe's story, shaping everything from the largest galaxy clusters to the smallest particles. And as we turn our attention to the role of black holes, we'll uncover even more ways that energy drives the evolution of the cosmos, connecting the smallest scales to the vast expanse of space. So, the next time you think about the universe, remember this. Even in the seemingly empty spaces between galaxies, energy is at work, shaping the cosmos in ways that are both subtle and profound. And as we continue to decode these cosmic fingerprints, we may find that they hold the key to understanding not just the universe's past, but its future as well. Now, let's tune into a cosmic whisper, a faint, almost imperceptible signal that carries the echoes of the universe's earliest moments. This is the cosmic neutrino background, a relic of the Big Bang that has been streaming through the cosmos for nearly 14 billion years. Unlike the light from stars or the glow of the cosmic microwave background, these neutrinos are ghostly particles slipping through matter almost undetected. But their presence is undeniable, and their story is one of the most profound in the history of the universe. To understand the cosmic neutrino background, picture the universe just 1 second after the Big Bang. At this moment, the cosmos was a seething, dense soup of particles and energy. Neutrinos, born in this chaotic environment, were among the first particles to break free, racing outward as the universe expanded and cooled. Today, these ancient neutrinos are everywhere, billions of them passing through you every second, yet they're so elusive that detecting them directly remains one of the greatest challenges in science. What makes these neutrinos so special is what they reveal about the universe's infancy. They're like cosmic time capsules carrying information about the conditions of the early universe. By studying them, scientists can piece together how energy flowed in those first moments, how matter clumped together, and how the seeds of galaxies and stars were sown. It's as if these particles are whispering the secrets of the cosmos, offering clues about its birth and evolution. But detecting this cosmic whisper isn't easy. Neutrinos interact so weakly with matter that they can pass through entire planets without a trace. To catch them, scientists rely on massive, ultra-sensitive detectors buried deep underground, shielded from other particles that might interfere. These detectors are like cosmic ears, listening for the faintest signals from the universe's earliest days. The cosmic neutrino background also plays a crucial role in shaping the universe's large-scale structure. In the early universe, neutrinos were so energetic that they streamed freely, smoothing out the distribution of matter and influencing how galaxies and clusters formed. Even today, their subtle gravitational pull continues to shape the cosmic web, the vast network of galaxies and voids that defines the universe's architecture. As we reflect on this ancient relic, one thing becomes clear. Cosmic energy isn't just a force that powers stars and galaxies, it's a thread that connects the universe's past to its present. From the ghostly whispers of neutrinos to the brilliant light of distant stars, energy is the language the cosmos uses to tell its story. And as we turn our attention to the universe's large-scale structure, we'll uncover even more ways that this energy shapes the cosmos, weaving a tapestry of complexity and beauty that stretches across billions of light years. So, the next time you think about the universe, remember this: even in the quietest corners of space, there's a hidden energy at work, a force that connects the smallest particles to the grandest galaxies. And as we continue to unravel its mysteries, we may find that the answers to some of the universe's greatest questions lie in the whispers of these ancient neutrinos. What if the universe left behind a cosmic echo, a ripple in space that reveals how energy shaped its earliest moments? This brings us to our 47th revelation: Baryon acoustic oscillations, subtle imprints of cosmic energy that have been traveling through the cosmos for billions of years. These oscillations are like the universe's heartbeat, a rhythmic pulse that tells the story of how matter and energy interacted in the moments after the Big Bang. To understand Baryon acoustic oscillations, picture the early universe as a dense, hot soup of particles and energy. In this chaotic environment, pressure waves similar to sound waves rippled through the cosmic plasma, compressing matter in some regions and leaving it sparse in others. When the universe cooled and became transparent, these ripples froze in place, creating a pattern of dense and sparse regions. Today, we see this pattern in the distribution of galaxies, which cluster along the peaks of these ancient waves like beads strung along invisible threads. But what makes these oscillations so important? They're a cosmic ruler, allowing scientists to measure the universe's expansion with incredible precision. By studying how far apart galaxies are in these ripples, astronomers can calculate how fast the universe is stretching. And here's where it gets fascinating. These measurements reveal the influence of dark energy, the mysterious force driving the universe's accelerated expansion. The spacing of these oscillations tells us not just about the universe's past, but also about its future, how fast it will grow and what role dark energy will play in its ultimate fate. Now consider this: the same cosmic energy that created these oscillations also influences the behavior of particles on the smallest scales. Just as ripples in a pond spread outward, affecting everything in their path, the energy of Baryon acoustic oscillations connects the largest structures in the universe to the tiniest particles. It's a vivid reminder that the cosmos is deeply interconnected, with energy flowing seamlessly from the quantum realm to the vast expanse of space. As we explore these cosmic echoes, one thing becomes clear: they're more than just relics of the past. They're active participants in the universe's story, shaping its structure and evolution over billions of years. And as we turn our attention to the behavior of particles, we'll uncover even more ways that energy weaves together the fabric of reality, connecting the smallest scales to the grandest galaxies. So, the next time you gaze at the night sky, remember this: the galaxies you see are part of a vast, rhythmic pattern, one shaped by the energy of the universe's earliest moments. And as we continue to decode these cosmic ripples, we may find that they hold the key to understanding not just the universe's past, but the forces that will shape its future. Imagine standing in a dimly lit room, watching as shadows stretch and shift across the walls. Now, picture the universe as that room, and the cosmic microwave background, the oldest light in existence, as the faint glow on those walls. But there's a twist. As the universe expands, driven by the mysterious force of dark energy, the shadows on these cosmic walls don't just sit still. They shift, subtly changing in ways that reveal the invisible hand of cosmic energy at work. This is the integrated Sachs-Wolfe effect, a phenomenon that shows how the universe's expansion leaves its mark on the ancient light of the Big Bang. Here's how it works. As light from the cosmic microwave background travels through the cosmos, it passes through regions of space where gravity's pull varies. In the early universe, when matter was densely packed, gravity dominated, and light photons lost energy as they climbed out of these deep gravitational wells. But as the universe expanded, dark energy began to take over, stretching space and weakening gravity's grip. When photons pass through these regions today, they gain a tiny bit of energy instead. This shift creates subtle temperature fluctuations in the cosmic microwave background, like cosmic shadows that shift as the universe evolves. These shifts might seem small, but they're incredibly significant. They provide direct evidence of dark energy's influence on the universe's expansion, confirming that the cosmos isn't just growing, it's accelerating. The integrated Sachs-Wolfe effect is like a cosmic fingerprint, revealing the presence of dark energy in the faintest ripples of the universe's oldest light. To make this even more vivid, think of it like this. Imagine you're hiking up a mountain. As you climb, the air thins and you feel the effort in your legs. But suddenly, the mountain starts to flatten and the air becomes easier to breathe. This change reflects the integrated Sachs-Wolfe effect. The photons, like hikers, experience a shift in their journey as the universe's expansion alters the landscape of gravity. The implications of this effect are profound. By studying these subtle shifts, scientists can map the distribution of dark energy across the universe, piecing together how it has shaped the cosmos over billions of years. It's a reminder that even the faintest whispers of light can carry the echoes of cosmic energy, connecting us to the deepest mysteries of the universe. And speaking of energy, while dark energy shapes the universe on the grandest scales, another form of cosmic energy is much closer to home, powering the very heart of our solar system. The sun, that brilliant ball of light in our sky, is a cosmic powerhouse, and its story is just as fascinating as the shadows that dance across the cosmic microwave background. But that's a story for another moment, as we continue to explore the incredible ways energy shapes the universe, from the largest structures to the smallest particles. As we stand on the brink of a new era in cosmology, one question looms large. What will we discover next? The future of our understanding of cosmic energy is brighter than ever, thanks to groundbreaking missions and technologies poised to unveil secrets hidden in the farthest reaches of the universe. At the forefront of this revolution is the James Webb Space Telescope, a marvel of engineering designed to peer deeper into space and further back in time than ever before. With its ability to detect infrared light, Webb will reveal the earliest galaxies, the birth of stars, and even the atmospheres of distant exoplanets. It's like having a time machine that can show us the universe's first whispers of light, offering clues about how cosmic energy shaped its infancy. But Webb isn't the only tool in our cosmic toolkit. The Vera Rubin Observatory, set to begin operations in the coming years, will conduct the legacy survey of space and time, mapping the entire visible sky every few nights. This unprecedented project will capture the fleeting light of supernova, track the movement of asteroids, and uncover the subtle effects of dark energy on the universe's expansion. Imagine it as a cosmic detective, piecing together the clues left behind by the universe's most mysterious forces. Together, These missions promise to transform our understanding of cosmic energy, revealing its role in everything from the formation of galaxies to the ultimate fate of the cosmos. What makes these upcoming discoveries so exciting is their potential to challenge or confirm our current theories. Will we find evidence of new particles or forces that reshape our understanding of dark energy? Could we uncover the origins of the cosmic web or even detect signatures of other universes? The possibilities are as vast as the cosmos itself, and each new observation brings us closer to answering some of the most profound questions in science. And while these missions focus on the grand scale of the universe, they also remind us of how cosmic energy influences the smallest details of galactic behavior. From the way galaxies cluster and collide to the intricate dance of stars within them, energy is the invisible hand guiding their every move. It's a reminder that the universe is a deeply interconnected system, where the largest structures and the tiniest particles are woven together by the same fundamental forces. As we look ahead to these exciting discoveries, one thing is certain: the story of cosmic energy is far from over. With each new observation, we're not just learning about the universe, we're uncovering the forces that connect us to the very heart of existence. And as we turn our gaze to the behavior of galaxies, we'll see how this energy continues to shape the cosmos, driving its endless cycle of creation and transformation. So, what will we discover next? The answer lies in the stars and in the energy that flows through every corner of the universe, waiting to reveal its secrets to those who dare to look. The search for extraterrestrial life has always been one of humanity's most profound quests, a journey that takes us to the farthest reaches of the cosmos in pursuit of answers. But what if the key to finding life beyond Earth lies not just in the chemistry of distant planets, but in the very energy that flows through the universe? This brings us to our 50th and final revelation. Cosmic energy might hold the clues to discovering life beyond our own world, and it could even redefine what we consider life to be. Think of cosmic energy as a universal beacon, a signal that transcends the boundaries of planets and stars. Just as sunlight fuels life on Earth, energy from distant stars and galaxies could be the lifeblood of ecosystems we've yet to imagine. Across the cosmos, energy takes countless forms, from the warmth of a star to the radiation emitted by black holes, and each one could provide the spark needed to sustain life in ways we've never considered. Take, for example, the potential for energy-based life forms. On Earth, life as we know it depends on carbon-based chemistry. But what if life elsewhere doesn't rely on molecules at all? Imagine beings that thrive on pure energy, drawing sustenance from the magnetic fields of neutron stars or the intense radiation of quasars. These hypothetical life forms might exist in environments too extreme for carbon-based organisms, harnessing cosmic energy in ways that challenge our understanding of biology itself. Even for more familiar forms of life, energy is the cornerstone of survival. On planets orbiting distant stars, the energy from their suns could drive photosynthesis, weather systems, and even the evolution of complex organisms. The search for extraterrestrial life often focuses on finding Goldilocks planets, worlds with conditions just right for liquid water. But water is only part of the equation. Without a steady source of energy, whether from a star, a planet's core, or even tidal forces, life as we know it couldn't exist. This raises a fascinating question: could cosmic energy itself be a sign of life? Just as humans have used radio waves and lasers to communicate, advanced civilizations might harness energy to send signals across the cosmos. Imagine a distant star flickering in a deliberate pattern, or a burst of gamma rays carrying encoded messages. These energy-based signals could be the cosmic equivalent of a lighthouse, guiding us toward civilizations far beyond our own. As we ponder these possibilities, it's worth remembering that cosmic energy doesn't just sustain potential life, it also shapes the universe on the grandest scales. From the formation of galaxies to the clustering of matter, energy is the driving force behind the cosmos' evolution. And just as it weaves together the fabric of the universe, it may also hold the key to unlocking the mysteries of life itself. So, as we conclude our journey through 50 mind-blowing revelations about cosmic energy, let's take a moment to marvel at its profound role in shaping not just the universe, but the potential for life within it. Whether through the warmth of a star, the glow of a distant galaxy, or the faint hum of a quantum field, energy is the thread that connects us to the cosmos and to the possibility that we are not alone. As we reach the end of this cosmic journey, it's time to reflect on the 50 mind-blowing revelations that have reshaped how we see the universe. From the invisible threads of the cosmic web to the explosive power of gamma-ray bursts, each discovery has unveiled a new layer of the cosmos, revealing the profound role of cosmic energy in shaping everything, from the smallest particles to the largest galaxies. These insights don't just deepen our understanding of the universe, they challenge us to rethink our place within it. Think about it. Cosmic energy isn't just a force out there in the stars, it's woven into the fabric of existence itself. It powers the sun that lights our days, fuels the stars that guide our nights, and even influences the mysterious dark energy that stretches the universe ever outward. These revelations remind us that the universe is far more dynamic and interconnected than we often realize. Every atom in your body, every beam of light that touches your skin, is part of this vast cosmic dance, driven by the same energy that shaped the universe from its very first moments. What makes these discoveries so extraordinary isn't just the science, it's the way they inspire wonder. They show us that the universe is full of mysteries waiting to be uncovered, from the quantum ripples in the vacuum of space to the distant echoes of the Big Bang. Each revelation is a reminder that the cosmos is not just a collection of objects in space, but a living, breathing system, constantly evolving and full of surprises. As we stand on the edge of these cosmic truths, it's impossible not to feel a sense of awe. The universe is vast, complex, and often beyond our comprehension, but that's what makes it so captivating. Every question we answer leads to new mysteries, and every discovery sparks new curiosity. It's a journey that never ends, one that invites us to keep exploring, keep questioning, and keep marveling at the beauty of the cosmos. To close, let's remember the words of Carl Sagan. Somewhere, something incredible is waiting to be known. The universe is full of wonders, and cosmic energy is the key that unlocks them. So keep looking up, keep asking questions, and keep exploring the infinite possibilities that lie beyond the stars. What do you think about these cosmic revelations? Which one amazed you the most? Let us know in the comments below. We'd love to hear your thoughts. And if you're as fascinated by the mysteries of the universe as we are, don't forget to subscribe for more cosmic discoveries. Together, let's continue unraveling the secrets of the cosmos, one revelation at a time.